the silent depths of space, far from the blue glow of our Earth, a vast cosmic ocean of stars stretches out in every direction. Countless suns shimmer like distant lanterns in the dark, each one a beacon in the void. Nebulas float like colourful clouds, softly glowing in hues of red, blue, and purple. Nurseries where new stars are born. The Milky Way arches across the sky as a pale river of light, a gentle band made of billions of stars. In this tranquil expanse, time seems to slow down, and the universe reveals itself in quiet, subtle ways, inviting us to explore its mysteries. We leave the familiarity of Earth far behind, drifting further into this ocean of night. Occasionally, a faint nebula or a cluster of stars comes into view, like an island in the sea, then recedes. Galaxies beyond our own loom as distant lantern glows, each containing billions more stars. The scale of it all is almost impossible to fathom, an expanse so vast that our minds can only wander through it in wonder. Amid the gentle darkness, we realize that every point of light has its own journey. Stars are born, live their lives, and eventually fade away. As we glide through a quiet region between spiral arms, our attention is drawn to a solitary star, larger and older than most. It has a subtle reddish hue, a sign that it's in the late autumn of its existence. This star has been shining for millions of years, but now its light wavers slightly as its internal fires wane. We find ourselves slowly orbiting this bloated giant, witnessing from a safe distance the twilight of a sun. Unbeknownst to the tranquil surrounding space, this star is approaching a transformative moment. In its core, the last reserves of fuel are nearly spent, and the delicate balance that has sustained it is about to tip. In the stillness, we watch and wait, sensing that we stand at the threshold of something profound. The calm is a prelude to an event that will both end the star's life and give birth to one of the universe's most mysterious objects. In the silence of the cosmic night, a giant star prepares for its final act, and we, as observers, are about to witness the first step on our journey into the realm of black holes. Amid this sea of stars, each shining point has its own story. Stars live for millions or billions of years, quietly burning their fuel and lighting up the darkness around them. But even stars are not eternal. In the great cosmic dance, there comes a time when a massive star's life reaches its end. When a star much larger than our sun has exhausted the nuclear fire at its core, it can no longer hold up against its own gravity. We watch in our mind's eye as such a star grows old and transforms. It swells into a red giant, bloated and luminous, casting a ruddy glow across a nearby nebula. Its core contracts as fuel runs out, and in one final, magnificent act, the star collapses inward. The sudden collapse triggers a titanic explosion, a supernova, a brief moment when the star shines with the brilliance of 10 billion suns. In that instant, the surrounding space is bathed in an intense flash. We witness the star's outer layers blasting off into the void, forming a rapidly expanding shell of glowing gas. Colours of every hue, from brilliant blue-white near the core to deep crimson at the edges, spread out like a celestial flower blooming in time-lapse. Any nearby worlds would be scorched by the fierce energy, and the nebula around the star is suddenly illuminated, sculpted by the force of the explosion. For a few weeks, This dying star outshines everything else in its galaxy. Its outer layers are hurled into space, enriching the cosmic nebulae with heavy elements forged in the star's heart. But what remains behind at the center is not empty. The heart of the star, once a ball of hot plasma, has been crushed to something entirely new. In some cases, if the star was just moderately heavy, this core becomes an incredibly dense neutron star, an object so compact that its atoms are squeezed together into a mass of neutrons. A neutron star is tiny, perhaps only the size of a city, yet heavier than our sun. In fact, a mere teaspoon of its material would weigh billions of tons on Earth, more than a mountain. It shines dimly with leftover heat and spins rapidly, sometimes flashing beams of light across space like a lighthouse, a pulsar signaling its presence. However, if the star was even more massive, nothing can stop the collapse. The core's gravity overwhelms all forces, and it continues to shrink past even the density of a neutron star. It vanishes from view behind a dark curtain, a boundary beyond which not even light can escape. In that moment, a black hole is born. Where once there was a brilliant star, now there is a patch of darkness in the cosmic ocean. The material of the star has been compressed into an almost inconceivably small space, creating gravity so strong that it traps everything, even rays of light, that come too close. This newborn black hole is like a silent whirlpool in space-time, an invisible vortex left in the aftermath of the supernova's fireworks. All around, the debris of the exploded star drifts away into space, a glowing cloud that will one day become part of new stars and planets. But at the center, the black hole remains, unseen, yet exerting its influence on the surroundings. It is a quiet remnant of a violent event, a sort of cosmic phoenix rising not as a new star, but as a gravitational ghost of the star that once was. The black hole itself is unlike any other object. It is essentially a region of space where gravity has become overwhelming. We cannot see the black hole directly because no light or any other signal can escape from within its grasp. Instead, what defines the black hole is a boundary called the event horizon, the point of no return. Anything that crosses this invisible boundary is lost to the outside universe forever, drawn inexorably toward the center of the black hole. The event horizon isn't a physical surface. It's more like an imaginary sphere around the black hole, marking where escape becomes impossible. Outside this sphere, light can still orbit or escape if it's far enough away. But once light or matter passes the event horizon, it's as if they have fallen over a waterfall in space, and there is no climbing back out. To an outside observer, the event horizon appears completely black, since nothing that happens inside can be seen directly. It's a one-way membrane in the fabric of space-time. Things can fall in, but nothing comes out. That is why we call it a black hole, a hole in space that swallows light and matter, leaving behind a dark void. At the very center of a black hole, hidden deep within, our current understanding of physics says there lies a singularity, a point of infinite density. This singularity is the crushed core of the original star, or whatever material formed the black hole, compressed to a point so small that it defies imagination. All the mass is concentrated there, which is what causes the immense gravitational pull. In truth, no one knows exactly what the singularity is like, or if it is even a point at all, because the laws of physics as we know them break down under such extreme conditions. Space and time as concepts may cease to have their usual meaning at the singularity. What we do know is that as one moves closer, to the black hole's center. Gravity grows stronger and stronger. Near the event horizon, the pull of gravity is almost infinitely strong, enough to bend rays of starlight, slow down clocks, and stretch objects apart. The environment around a black hole is a warped landscape of space and time, where the usual rules seem to blur. It is a place where our intuitions falter, a mysterious realm predicted by Einstein's theory of general relativity, yet so extreme that it remains unobserved directly beyond that horizon. Despite being invisible directly, black holes make their presence known in other ways. Their gravity influences the orbits of nearby stars, and their immense pull can heat up gas around them until it glows. In a sense, a black hole is like a hidden engine in space, unseen, but its effects can be dramatic and far-reaching. To truly understand this enigmatic object, we must venture, at least in thought, closer to its edge, to see how the universe changes in the vicinity of a black hole. Imagine now that we drift closer to this black hole as an intrepid explorer or a floating probe. What would we experience near that point of no return? One of the most unsettling effects is on time itself. According to Einstein's relativity, time flows differently in strong gravity. If we hover just outside the event horizon, time for us would slow down relative to the rest of the universe. To a distant observer watching our approach, it would appear as if we are moving ever more slowly as we near the event horizon. In fact, from their viewpoint, we would never quite appear to cross the boundary at all. We would seem to freeze in place right at the edge, fading and dimming as the light we send back becomes weaker and more red-shifted. This happens because the light leaving from near the event horizon loses energy, climbing out of the deep gravity well, its wavelength stretching into the red and beyond, eventually becoming invisible. To the outside world, an object falling into a black hole seems to take an eternity to fully disappear, slowly dimming and reddening until it vanishes from sight. But what of our own experience, if we ourselves are the ones falling in? Relativity tells us that our experience can be very different. If we, as the brave explorer, were to cross the event horizon, we might not notice anything extraordinary at the exact moment of crossing. There is no physical border marking it, no sudden jolt or barrier. One moment we're outside, the next moment we're inside, with nothing particularly dramatic locally to signal that we've passed that ultimate threshold. Time for us would feel normal. Our clocks tick seemingly at the usual rate, and our heartbeat would carry on as we plunge deeper. Yet even as we feel normal in our own frame, we cannot escape the fate that awaits deeper inside. From our perspective, we fall inexorably towards the center. The outside universe above us would start to look strange. If we glance back outward, towards where we came from, we might see the entire universe's history playing out faster. Distant stars and galaxies would appear to speed up, as if time outside is racing forward. In principle, if one could survive long enough while falling in, one might see the far future of the universe unfold in a matter of moments as the outside world's time speeds by from our plunging vantage point. This is all a consequence of the relativity of time. The stronger the gravity, or the faster one moves, the slower time passes relative to elsewhere. However, survival is a big if. As we descend, another phenomenon begins to take hold, the stretching of space and our own bodies by gravity's gradient. This is the effect known colloquially as spaghettification, which we will soon explore. But first, consider how extraordinary this time dilation is. Black holes allow nature to twist time into knots. Near a black hole, what might be a brief minute for the falling observer could be years or centuries outside. In a way, a black hole can act as a kind of one-way time machine to the future. For the one falling in, there is no coming back to tell the tale. But they travel into the future of the universe, as seen from their perspective, looking outward. This interplay of perspectives, an outside observer seeing someone slow and fade, and the falling person experiencing a normal passage of time and witnessing the universe's fast forward, is one of the mind-bending aspects of black hole physics. It shows us how fluid and relative time can be under extreme conditions, adding to the mysterious aura that black holes cast across the cosmos. Now, as we venture closer and closer to the center of the black hole, the gentle experience of crossing the horizon gives way to something more destructive. The gravity at our feet is now significantly stronger than the gravity at our head, if we are falling feet first. This difference in pull between 2 points, the tidal force, starts to stretch us. Near smaller black holes, these tidal forces become lethal well before an object even reaches the event horizon. An astronaut approaching a small black hole would be pulled apart long before crossing into the darkness. The term spaghettification paints an evocative picture. Any object, whether a human or a spacecraft or a stream of stellar gas, would be stretched into a long, thin strand by the black hole's gravity. The nearer part of the object is pulled harder than the farther part, so it continuously stretches. For a stellar mass black hole, perhaps a few times the mass of the Sun, this effect is extraordinarily strong at close range, ripping apart even atoms as they plummet inward. However, if the black hole is very large, such as the supermassive black holes found in galactic centers, something counterintuitive happens. The tidal forces at the event horizon can be much milder. Paradoxically, the more massive the black hole, the larger its event horizon, and the more gradually gravity changes across it. This means an observer could cross the event horizon of a supermassive black hole without immediate tidal death. In fact, they might not feel severe stretching until much later, deeper inside. For instance, the supermassive black hole at the center of our galaxy, with a mass of a few million suns, has an event horizon radius of about 17 million kilometers. At that scale, an astronaut falling through might pass the horizon unharmed initially, because the change in gravity from head to toe at the horizon could be relatively small. Only when they approach closer to the central mass will the stretching intensify to fatal levels. Thus, in theory, one could imagine falling into a sufficiently large black hole and surviving the entry. It would be a rather uneventful crossing, and one might even enjoy a brief, surreal period of floating in apparent calm after having passed the horizon, with nothing seeming amiss locally. But this calm is deceptive. As one gets closer to the singularity, eventually the tidal forces will increase beyond anything that can be withstood. Even for a supermassive black hole, at some point, before reaching the very core, any traveller would be stretched and compressed by gravity into a ribbon of matter. No known material or technology could withstand that infinite pull near the singularity. This dramatic stretching illustrates how space near a black hole is incredibly curved. It's not just pulling on objects uniformly, it's warping space to different degrees at different points. And so, while from afar, a black hole might appear as a simple dark sphere, up close, it is a complex gradient of gravitational intensity, quietly but relentlessly pulling anything nearby into its embrace. The fate of anything that falls in is to be ultimately torn and added to the mass of the black hole. In a sense, the black hole grows slightly with each piece of matter it consumes. Every asteroid, star, or ray of light that disappears past the horizon increases the black hole's mass and its gravitational influence just a little more. Over eons, black holes can gain significant weight through this process, especially if they reside in busy regions of space with lots of material to feast upon. As we contemplate this journey to the center, we reach the limits of what physics can currently describe. The final fate of our hypothetical traveler, and of any matter that falls in, is shrouded behind the veil of the event horizon. Classical physics insists that all paths lead to the singularity, a region of infinite density and zero volume at the very core of the black hole. But infinities like this are usually a sign that our theories have broken down. To truly know what happens in those final moments, as one approaches the singularity, we would need a theory that merges gravity with quantum mechanics. A theory of quantum gravity that remains one of the great challenges of modern science. Some scientists suspect that, instead of a point of infinite density, there may be something else at the heart of a black hole. It could be that quantum effects create a highly compressed but finite object or region, something that replaces the singularity when gravity and quantum forces are both taken into account. Ideas range from a core made of exotic quantum matter to the notion that the singularity might be a bridge to another place, or even another universe. At this point, these ideas are speculative. The truth remains hidden behind the horizon. From our perspective outside the black hole, safely observing in thought, we cannot see beyond the event horizon to get any answers. It's as if information itself is sealed away once inside. Whatever happens in those extreme depths, it ceases to have influence on the wider universe, at least directly. The black hole's exterior can only tell us a few things: its mass, its spin, and its electric charge, if any. Physicists often say that black holes have no hair, meaning that, aside from those basic properties, all other details of what fell in are lost to our view. Whether those details are truly destroyed or somehow encoded subtly is a question we will return to later. For now, we are left with a profound mystery at the black hole's core. The singularity stands as a reminder of how much we still don't understand. It is a place where our familiar concepts of space and time break apart. Some describe it as a tear in the fabric of reality, others as a doorway to the unknown. Yet, because no information can escape from within, the interior of a black hole remains one of the most enigmatic realms in the cosmos. We can only infer and imagine what transpires in that lightless abyss. While our fallen traveller's story cannot be told beyond a certain point, we, as observers from outside, can still learn a great deal about black holes from their behaviour and effects on their surroundings. So let us step back out of the blackness now and look around the black hole from a safe distance to see how it appears to the rest of the universe. From a distance, how do we recognize a black hole is there at all? If it's truly black, one might think it would be completely invisible against the dark background of space. In fact, an isolated black hole, with no nearby matter, is extremely hard to detect. It would simply be a silent gap in the starry sky. However, the presence of a black hole can be inferred by its gravitational effects. For instance, we might notice a star moving in a strange, fast orbit around an unseen mass, as if circling a phantom. This is how the supermassive black hole at the centre of our Milky Way was discovered. By observing stars whipping around an apparently empty spot, astronomers deduced a huge mass, about 4 million suns worth, confined in a tiny area. Only a black hole could explain that. Another clue comes from the way black holes can bend light. Gravity can act like a lens, curving the path of light passing near a massive object. Around a black hole, this effect is extreme. Starlight passing close to the black hole is bent into arcs and rings. If we look towards a black hole with a bright galaxy or star field behind it, we might see a distorted halo or ring of light, a so-called Einstein ring. In the most dramatic case, if we were directly behind a black hole relative to a bright source, we would see the light from that source warped into a perfect circle around the black hole's silhouette. So even though the black hole itself emits no light, its gravitational presence can create a kind of eerie visual imprint by warping the light of background stars into surreal patterns. Additionally, any light or radiation emitted just outside the event horizon can still reach us, although it is affected. Light originating near the horizon loses energy climbing away. It becomes redshifted to longer wavelengths. High-energy light might shift down to visible light to infrared, and so on. Eventually, if the light loses enough energy, it could become radio waves. This gravitational redshift means that if we could see an object glowing right outside the event horizon, it would appear dimmer and redder than it truly is, drained by the black hole's gravity. By the time any signals from near the horizon reach a distant observer, they carry the telltale signs of this gravitational influence. Thus, a black hole might announce itself indirectly, through the frantic orbits of nearby stars, through rings and arcs of bent light, and through faint, reddened glimmers from matter at the brink of oblivion. It's awe-inspiring to reflect that black holes were once considered mere theoretical peculiarities. In the mid-20th century, some scientists even doubted they would ever be found. But bit by bit, evidence emerged. In the 1960s, the discovery of intense X-ray sources, such as one named Cygnus X1, suggested a hidden black hole feeding on a companion star. In later decades, astronomers observed stars near the Milky Way's center moving at staggering speeds, eventually convincing the scientific community that a supermassive black hole must be there. Fast forward to 2015, detectors on Earth sensed gravitational waves from merging black holes, and in 2019 came that first iconic image of a black hole's shadow. Within a human lifetime, black holes went from speculative math to concrete reality, a testament to the power of human curiosity and ingenuity. Yet, despite seeing and hearing them indirectly, these objects remain as mysterious and majestic as ever when we contemplate them. But when a black hole has matter actively falling into it, it is far from quiet or invisible. In fact, such a black hole can become one of the brightest objects in the universe in its immediate vicinity. To understand that, we need to examine what happens when a black hole is feeding. When a black hole has a supply of gas, dust, or other stars nearby, it can pull this material toward itself. As matter spirals into a black hole, it doesn't usually fall straight in. Instead, it forms a swirling disk around the black hole called an accretion disk. This disk is made of extremely hot, rapidly rotating plasma. Friction and the immense gravitational forces heat the disk to incredible temperatures. We might picture it as a brilliant, flat ring of light encircling the dark shadow of the event horizon. In reality, the colors would span beyond the visible. Much of the energy is emitted as X-rays and gamma rays, the signatures of very hot gas. This glowing accretion disk can shine with great intensity. If we were to observe it from afar, we would see something extraordinary. A dark circle, the black hole's silhouette, surrounded by a luminous halo of swirling light. In fact, scientists have captured an image of such a scene. In 2019, astronomers using a network of radio telescopes across Earth produced the first direct image of a black hole's surroundings. It revealed a bright, fuzzy ring of orange-colored light with a dark center, the shadow of a supermassive black hole in a galaxy far away, 55 million light-years distant. That ring is the light from the accretion disk, bent and amplified by the black hole's gravity, and the dark center is roughly where the event horizon lies, beyond which light cannot reach us. Seeing this was a remarkable confirmation that these mysterious objects truly exist, as Einstein's theories predicted. It is remarkable that an object once thought by some to be purely theoretical was now captured on camera, its eerie shadow matching the expectations set by physics. Around some black holes, especially supermassive ones, the accretion disk can be accompanied by jets, narrow beams of particles and energy that shoot out from the poles of the black hole at nearly the speed of light. These jets are powered by the black hole's magnetic fields and rotation. As the disk spirals in, it twists magnetic field lines tightly. Like a spring uncoiling, these field lines can fling particles outwards along the poles. The result is a pair of opposed jets blasting into space above and below the disk. These jets can carry matter thousands of light years away and make the environment of a feeding black hole even more dramatic. To a distant observer, an actively feeding black hole, often called an active galactic nucleus or quasar when it's the core of a distant galaxy, is anything but black. Quasars are among the brightest beacons in the universe, visible across billions of light years. We see them as extremely luminous objects, often outshining the entire galaxy that hosts them. What we're seeing is not the black hole itself, but the energy released by matter in the act of falling into the black hole's gravitational grip. The sight of an active black hole is one of stark contrast. If we could get a safe view up close, we'd see a swirling maelstrom of light in the disk, perhaps orbiting at nearly the speed of light at the inner edge. We would see space around it bent, such that the far side of the disk is lensed above and below the black hole, creating a warped image of the disk that appears to wrap around the black hole's darkness. The jets, if present, would stab out into space, glowing in radio waves and visible light, a cosmic lighthouse marking the presence of a voracious black hole. And yet, if we were to fall past the event horizon from within that disk, all that light and fury would vanish from our view. We'd enter a realm of darkness again. It's fascinating to think that some of the brightest things we observe in the universe, quasars and X-ray binaries, are simply the heralds of a black hole that itself remains hidden behind a one-way door. The energy released before matter crosses that threshold is the last gasp of the infalling material, and it can be immensely powerful. Not all black holes have such fireworks going on. Many are relatively quiet. A black hole with nothing to consume is nearly undetectable. Only when a stray cloud of gas or an unlucky star wanders close does the show begin anew. When that happens, the black hole awakens, the accretion disk ignites, and potentially jets form. We can think of black holes as sleeping giants that sometimes feast and flare up. In the vast calm of space, a dormant black hole is invisible and silent. But a feeding black hole becomes a cosmic engine of high-energy phenomena. These processes remind us that black holes, while destructive in their consumption, also play a creative role in the cosmos. The energy they release in feeding can influence their surroundings. Jets can stimulate star formation in distant clouds, or, alternatively, blast away material that would have formed new stars, thus regulating the growth of galaxies. Black holes are an integral part of galactic ecosystems, quietly shaping the evolution of galaxies over millions of years by their sporadic feasts and famines. For example, a burst of energy from an active galactic nucleus can push away the raw material needed for star formation, slowing the growth of new stars in the galaxy. Yet that same burst might send shockwaves into distant interstellar clouds, compressing them and perhaps triggering new stars to form further out. In this way, the black hole's influence can both hinder and foster creation, acting as a cosmic gardener, pruning here and seeding there. Black holes come in different sizes. The ones formed from dying stars are typically a few times up to maybe tens of times the mass of our Sun. Those are often just a few kilometers across in diameter, smaller than many cities, yet containing the mass of an entire star. These stellar mass black holes are scattered throughout galaxies, including our own Milky Way. They might form in the aftermath of supernovae, as we saw, or even from direct collapse of a star without an explosion. We have found many candidates by observing X-ray emissions from binary star systems, where one star is invisible, yet pulling gas from a companion, shining brightly in X-rays as the gas falls in. There is also evidence for black holes of intermediate sizes, more massive than a typical star's remnants, but not as massive as the monsters in galactic centers. These intermediate mass black holes could weigh hundreds or thousands of suns. Their origin is a bit mysterious. They might form from the merger of several smaller black holes, or from primordial conditions in star clusters. They are harder to find, but a few have been hinted at, perhaps in dense star clusters or dwarf galaxies, where something is just heavy enough to be a black hole of that scale. At the top of the scale are the supermassive black holes, residing in the cores of most galaxies. These can range from millions to billions of times the mass of our Sun. The one in our Milky Way, called Sagittarius A, is about 4 million solar masses. Others, like the black hole in the galaxy M87 which was imaged, are around 6.5 billion solar masses. Despite their enormous mass, their density can be lower on average than that of a smaller black hole because their radius, the event horizon size, scales with mass. For example, M87's black hole has an event horizon that could encompass our entire solar system. How do these supermassive black holes form? It's an open question in astrophysics. Some theories suggest they started as smaller seed black holes, maybe around 100 solar masses, formed from the first generation of stars, or from dense star cluster collisions. These seeds, over billions of years, consumed gas and merged with other black holes to grow larger and larger. Another idea is that in the early universe, huge clouds of gas collapsed directly into massive black holes, without fragmenting into stars first. A direct collapse scenario that could jumpstart a black hole to be thousands or 100,000s of solar masses right away. Over time, those could grow to the giants we see now. Yet, even these theories struggle to explain some observations, because we find supermassive black holes very early in the universe's history, when galaxies were young. Somehow, they grew quickly. It's humbling to realize that at the center of nearly every galaxy, including our own, lurks one of these supermassive black holes. Most of the time, they are quiet. The one in the Milky Way is relatively dormant, occasionally nibbling on a bit of gas and flickering faintly in X-rays. But when galaxies collide, or when a lot of material falls into the center, these black holes can ignite into quasars or active nuclei, as bright as the entire galaxy. They likely play a key role in shaping their host galaxies, regulating star formation, and acting as central anchors that keep the galaxy's stars in orbit. Between the smallest micro black holes, if any exist, and the largest supermassive ones, black holes present a continuum of scale, all obeying the same basic principles of gravity and relativity. Standing near any of them would be perilous, and yet all of them contribute to the grand cosmic tapestry. From the tiny unseen remnants of collapsed stars to the behemoths that sit in galactic thrones at the centers of cosmic cities of stars. There is even speculation about black holes at the very smallest and largest extremes beyond what we have clearly detected. On the small side, some scientists have proposed the existence of primordial black holes. Black holes that might have formed in the early universe, not from stars, but from the high-density fluctuations just after the Big Bang. These primordial black holes could, in theory, have a wide range of masses, from tiny ones smaller than a mountain to ones hundreds of times the Sun's mass. The tiny primordial black holes, if they formed, might have already evaporated by now, a concept we will discuss soon, but larger ones could still be roaming the cosmos. Some have even wondered if such black holes might account for some portion of the mysterious dark matter that makes up much of the universe's mass. So far, however, we have no definitive evidence that primordial black holes exist. They remain an intriguing idea, a what-if left over from our universe's youth. On the other extreme, the largest black holes we know of tip the scales at tens of billions of solar masses. These leviathans sit in the hearts of the most massive galaxies and galaxy clusters. How such colossal black holes came to be is another cosmic puzzle. They might be the result of numerous mergers of galaxies, and thus mergers of black holes, over time. Or perhaps they had very head start seeds in the early universe. One example is the black hole in the galaxy Messier 87, the very one imaged in 2019, which is billions of solar masses. Another even more extreme example is the quasar TON 619, which observations suggest harbours a black hole of around 66 billion solar masses, a truly unfathomable mass concentrated in one place. These supermassive black holes in the far cosmos give us a glimpse of just how far the growth can go. Whether small or huge, each black hole is a point where nature has done something extraordinary, creating a region where gravity has dominated everything else. And across this spectrum, many of the phenomena, the event horizon, the deep gravitational well, the potential for an accretion disk and jets if material is present, remain similar in nature. It's as if black holes are a recurring theme, playing out on different scales like variations of a musical motif in the grand symphony of the universe. Sometimes, the cosmos arranges an even more dramatic event involving black holes. The merger of two black holes. Imagine two black holes that formed as a pair of massive stars in a binary system. Each star lived out its life and collapsed, leaving behind two orbiting black holes. Over time, they draw closer together, their orbits shrinking due to the energy lost emitting gravitational waves. The two dark orbs spiral around one another like twin dancers in a tightening embrace. As they draw nearer, they move faster, orbiting many times per second in the final moments. Eventually, they collide and coalesce into a single, larger, black hole. This merger is a cataclysm of pure gravity. No light comes directly from the collision. Unlike star collisions, there's no bright flash visible across space because the objects are purely black. But energy is released in a different form, gravitational waves, which are ripples in the very fabric of space-time. These waves spread outward from the merging black holes like the rings on water after a stone is dropped, except these rings are moving at the speed of light and carrying information about the violent dance that created them. For billions of years, these gravitational waves travel across the universe, growing fainter as they go. In recent times on Earth, we built instruments sensitive enough to detect them. In 2015, the LIGO Observatory sensed the first direct signal of such a wave. It was the subtle stretching and squeezing of space from two black holes merging about 1.3 billion light-years away. The signal lasted only a fraction of a second in our detectors, a faint chirp after computer processing, yet it told a profound story. Two black holes of about 36 and 29 solar masses had merged to form one of about 62 solar masses, with a few solar masses worth of energy released as gravitational waves. Since then, many more black hole mergers have been observed via gravitational waves, confirming that these events are not rare. Gravitational waves themselves are imperceptible to human senses. They cause distances to shift by tiny fractions on Earth, far too small for us to feel. But sophisticated instruments can measure these minute changes. The detection of gravitational waves from black hole mergers not only confirmed a prediction of Einstein's theory made a century before, but also opened a new way of observing the universe. We can now hear the universe's most massive mergers in the language of gravity. Each detection is like listening to black holes colliding in distant space, an almost ghostly way of sensing an event that produces no light. In a meditative sense, one can imagine these gravitational waves as a gentle cosmic humming that fills the universe, a background choir of space-time vibrations created by countless mergers over cosmic history. As they pass through us, they whisper tales of colliding black holes and neutron stars, events otherwise hidden from our eyes. The entire universe is silently reverberating with these notes, though only our most sensitive instruments pick them up. Black hole mergers are perhaps the ultimate union of these exotic objects. Two become one, and the result is a single black hole that quivers for a moment, ringing like a struck bell in gravitational terms, and then settles down, slightly larger and carrying on its existence. The final black hole that results has a smooth horizon, and after the merger, it quickly returns to a quiet state, carrying no evidence on its surface of the tremendous event that just took place, aside from its increased mass and spin. This again reflects that no hair property. The chaos of the merger doesn't leave a trace that an outside observer can discern once it's over. The black hole is as featureless as ever, just heavier and possibly spinning faster. These collisions and the resulting waves give us a deeper appreciation of the dynamic side of black holes. They aren't just static holes sitting eternally. They can move, orbit each other, and undergo powerful interactions. Yet all of it can happen with almost no electromagnetic spectacle. The grandeur is in the gravity itself. To human imagination, it's a bit like picturing two invisible whirlpools in the ocean merging into one, sending ripples across the water. Except here, the ocean is space-time itself, and the ripples carry energy across billions of light years. While black holes merging with each other release energy in gravitational waves, a black hole meeting a star creates a more traditional kind of spectacle, one that can be seen in light. If a star ventures too close to a massive black hole, the uneven gravity across the star can rip it apart in what is known as a tidal disruption event. Imagine a star like our Sun wandering near the giant black hole in a galaxy's core. As the star nears, the side closer to the black hole is pulled much more strongly than the far side. Eventually, the star can be torn into a stream of gas. Half of that gas might get flung out into space, while the other half falls into orbit around the black hole, forming a temporary accretion disk. From afar, we would witness a sudden flare of light as the star's gas heats up while being devoured. Over weeks and months, the feeding black hole shines brightly in ultraviolet and X-rays, then gradually fades as the last of the star's remnants swirl in. It's a violent and tragic end for the star, but it produces a beautiful burst of energy, visible across the cosmos. These events are rare for any given galaxy, perhaps happening only a few times in 100,000 years per galaxy. But with billions of galaxies out there, astronomers have managed to catch a number of these stellar deaths by black hole. The cosmos occasionally reminds us of the danger that lurks in those quiet galactic centers. However, to keep perspective, space is vast, and such close encounters are infrequent. Most stars live out their lives without coming near a black hole. But knowing that this fate is possible adds another layer to the mystique of black holes. Not only can they hide in plain sight and collide with each other invisibly, they can also dramatically announce themselves by destroying stars that stray too near. Yet even this cataclysmic process can be thought of in a calm, almost cyclical way. The star's material, once part of a shining sun, is absorbed into the black hole. In a sense, that material isn't gone from the universe. It's now part of the black hole's mass. Someday, far in the future, if that black hole ever evaporates or otherwise releases energy back, the essence of that star may be returned to the cosmos in some transformed way. Thus, the matter and energy continue their cosmic journey, changing forms from star to light to black hole mass, and possibly, eventually, to radiation again. Up to now, we have been considering black holes as essentially traps from which nothing escapes. But there is a subtle exception, a twist from the realm of quantum physics that suggests black holes are not completely eternal, nor completely black. In the 1970s, physicist Stephen Hawking theorized that black holes can slowly leak energy and mass through what is now called Hawking radiation. This is a very gentle and slow process, nothing like the energetic emissions of accretion disks or jets. Instead, it arises from quantum fluctuations that occur in empty space. According to quantum theory, even the vacuum of space is not truly empty. It teems with transient pairs of particles and antiparticles that pop into existence and then annihilate each other almost immediately, usually completely undetected, near the event horizon of a black hole. Hawking proposed that if such a pair forms just at the right place, one particle might fall into the black hole, while the other escapes before they have a chance to annihilate each other. To an outside observer, it would appear as if the black hole emitted a particle. The particle that fell in has negative energy relative to the outside and reduces the mass of the black hole, while the escaping particle carries away that energy into space. Over time, this process would cause the black hole to very slowly lose mass. It would evaporate, For a typical stellar mass black hole, the Hawking radiation is incredibly faint. The temperature of a black hole's Hawking radiation is inversely proportional to its mass, meaning large black holes emit at extremely low temperatures, far colder than the cosmic microwave background that fills space. So, a black hole of a few solar masses would take an almost unimaginably long time to evaporate, far longer than the current age of the universe. It would hardly lose any mass in all the billions of years since its formation, because it's receiving more energy from the cosmic background and any stray matter than it emits. However, if a black hole is very small, its temperature would be much higher and it would evaporate more quickly. A black hole about the mass of a small asteroid might emit radiation at a noticeable rate. Tiny black holes, if they were made, for instance, in particle collisions or as primordial relics, could evaporate on human or astronomical timescales that are short compared to star lifetimes. In their final moments, such black holes would shrink to extremely small sizes and then vanish in a burst of high-energy radiation, essentially exploding like a tremendous bomb, releasing the last of their mass energy. No such explosions have been observed, which suggests that if primordial mini black holes were created in the Big Bang, either they were rare, or have mostly already evaporated, or are just too massive to have finished evaporating yet. What Hawking radiation implies is that black holes are not completely one way forever. Given enough time, they can give back to the universe the mass energy that was confined within them. The catch is the timescales involved. A black hole of a few solar masses would take on the order of 10 to 67 years to evaporate, a number almost impossible to fathom, immensely larger than the age of the universe, which is 10 to 10 years. For the supermassive black holes, the evaporation time is even longer, effectively meaning they will be around for an inconceivably long future. Imagine the universe in this distant future. The galaxies as we know them have dimmed. First, in tens of trillions of years, the big, bright stars die out, leaving only faint red dwarfs glowing. Then after trillions more years, even those embers cease as the last stars exhaust their fuel. Planets, if any remain, wander cold and dark. The Milky Way, Andromeda, and other galaxies may have merged, and ultimately the orbits of leftover objects decay or fling apart in gravitational dances over quadrillions of years. The cosmos that was once full of starlight becomes a quiet shadow filled mostly with black holes and the remnants of stars like black dwarfs, cooled white dwarfs, and solitary neutron stars. This epoch, sometimes called the black hole era by cosmologists, is dominated by darkness, punctuated only by the gravitational presence of black holes. These black holes slowly, imperceptibly, lose mass via Hawking radiation. Picture them as extremely faint warm objects, glowing at temperatures barely above absolute zero, radiating feeble light into the cold void. Over truly stupendous timescales, even those slight radiations add up. A black hole, the mass of the Sun, would take 10⁻⁶7 years to evaporate. Compare that to the current age of the universe, around 10⁻⁻10 years, and it's mind-bogglingly larger. For the supermassive giants, add many more zeros. But time is relentless. In that far future, with nothing new being born, the only changes are decays and dissipations. One by one, black holes will evaporate. A small black hole might go first with a last burst of energy. Larger ones persist longer, but even they eventually shrink. As a black hole nears its final end, its Hawking radiation grows more intense, though for a stellar black hole, this would only happen near the very end after unimaginable eons. In its final seconds, it could flash like a cosmic firecracker, converting its remaining mass to a spurt of high-energy particles and light. If there were any observers at that time, which seems unlikely, they would see perhaps a brief glimmer where a black hole used to be, a last sigh of light. After the last black hole has evaporated, the universe would be incredibly empty. All that remains would be a thin haze of particles and photons, gradually cooling towards absolute zero, and possibly the dark fabric of space-time itself expanding ever further. The once majestic galaxy clusters and nebulae are long gone. The drama of stars and black holes has given way to stillness. It's a somber, yet profoundly awe-inspiring vision. A universe that began in bright fire ends in quiet darkness. Black holes, which were among the most enduring entities, ultimately give up their mass back to space. In a poetic sense, the information and material they held might return to the cosmos at the end, released in those final flashes. Some theories even propose a sort of rebirth as a white hole in the very end, to satisfy certain interpretations of quantum physics, though that remains speculation. For us, contemplating this distant fate is almost like a form of meditation on impermanence. Even black holes, the paragons of longevity and secrecy, are not truly eternal. The cycle of cosmic evolution continues until it, too, winds down. From the brilliant glow of starry epochs to the faint whispers of Hawking radiation, the universe undergoes a slow metamorphosis into night. In our current vibrant universe, all this is unimaginably remote. Yet, considering it broadens our perspective, it reminds us that we live in the youth of the cosmos, basking in starlight, while the old age of the universe will be a very different, quieter place, ruled by the presence and eventual absence of black holes. Such is the grand timeline of existence that black holes connect us to. From the past of collapsing stars to the far future of a nearly empty cosmos, they are a common thread. Hawking's insight also raised deep questions. If black holes evaporate and disappear, what happens to all the information about the objects that fell into them? This led to what's known as the black hole information paradox, a puzzle that ties together quantum physics, thermodynamics, and relativity, and challenges our understanding of how the universe preserves information. Let us delve gently into this information paradox, for it touches on the philosophical as well as the physical. In physics, information means the specific details of an object, the unique properties of all particles and fields that make up that object. A fundamental principle of quantum physics is that information is not destroyed. It may change form, but it's fundamentally preserved. This is related to the idea that the evolution of quantum systems is reversible. However, if something falls into a black hole, and the black hole eventually evaporates completely, it appears as if the information about that thing might be lost from the universe. The only thing the black hole's radiation seems to carry away is featureless thermal energy, with no trace of the detailed information that went in. This paradox has led to intense debates and theoretical research. One proposition is that perhaps information is not truly lost. Instead, it could be encoded in the Hawking radiation in an extremely scrambled form. Another idea is that the information might be stored on the event horizon itself, in microscopic quantum imprints, and released as the black hole evaporates, a concept that gave rise to the holographic principle. The holographic principle suggests that everything that happens inside a volume of space could be described by information stored on the boundary of that space, like a hologram encodes a 3D image on a 2D surface. In the context of a black hole, it implies that the 3D information of whatever falls in might be entirely encoded on the 2D surface of the event horizon, subtly influencing the Hawking radiation that comes off. If this holographic idea is true, it means that nothing ever truly disappears into a black hole in terms of information. It's just held in an almost unrecognizable way at the edge. In a strange way, the surface of a black hole would contain a kind of memory of all that fell into it, encrypted in the language of quantum geometry. Then, as Hawking radiation is emitted, those quantum correlations could carry the information back out, albeit in a form that would be practically impossible to decipher. The information paradox is not fully resolved even today, and it sits at the crossroads of our understanding. It tells us that black holes are not only objects of gravity, but also objects that test the laws of quantum mechanics at their extremes. The resolution may lie in a theory of quantum gravity or a deeper understanding of space-time. Some proposals even suggest that what we perceive as a singularity or interior might be effectively a hologram of the horizon's information itself, or that new physics, like wormholes or quantum connections, called Einstein-Rosen bridges between the inside and the outside, could come into play. For our meditative journey, we need not dive too deeply into the mathematics of it. Instead, we can appreciate the poetry of this situation. A black hole, the epitome of destruction and loss, may actually hold within it the key to preserving the essence of everything it consumes, weaving it into the very fabric of its being. In this way, nothing is truly lost, only transformed in hidden ways. It's a comforting thought, perhaps, that even in the absolute darkness, traces of what once was might still exist, waiting to be unraveled by the universe's subtle logic. This mystery of information nudges us naturally into more speculative territory. Perhaps what's inside a black hole, or what a black hole is connected to, is stranger than we imagined. Could it be that a black hole's interior is not an end, but a gateway of sorts? The idea of wormholes, white holes, and connections to other universes comes to mind. Concepts born both from serious science and creative imagination. Let us now turn to those possibilities, letting our curiosity roam beyond the horizon and into the realm of the speculative beyond that black holes hint at. The idea of wormholes comes naturally when we think about the extremes of black holes. Wormholes are hypothetical tunnels or shortcuts through space-time, often visualized as two ends of a tube connecting different regions of the universe. In a way, you can imagine space and time as a fabric that can bend and fold. If two distant points in space could somehow be brought together and connected, a wormhole would let one travel between them in a shorter time than it would take to go through normal space. In Einstein's theory of general relativity, wormholes are allowed as mathematical solutions. In fact, the simplest picture of a wormhole emerged from considering black holes themselves. In 1935, Einstein and his colleague Nathan Rosen explored the idea that what we call a Schwarzschild black hole solution, the mathematical description of a non-rotating black hole, could be extended to include a mirrored universe on the other side. The result was what came to be called an Einstein-Rosen bridge. Essentially, a wormhole connecting two universes or two distant parts of space-time. However, their particular solution turned out to be unstable and not traversable by objects. It pinches off if anything tries to pass through, but it planted the seed that maybe something like a wormhole could exist.
If a wormhole were to be traversable, meaning you could actually go in one end and come out the other, it would likely require some exotic conditions. The equations of general relativity suggest that an unheld wormhole throat would collapse too quickly. To hold it open, it might require negative energy or pressure, often called exotic matter.
Negative energy isn't something we encounter in everyday life, but quantum physics does allow for regions of space with less than the usual amount of energy. For example, in the Casimir effect between closely placed plates, some scientists speculate that if one could gather enough negative energy, one might stabilize a wormhole. This is very speculative and beyond current technology by a vast margin, but it's not outright forbidden by known physics. Now let's imagine, in a very fanciful way, that a stable wormhole exists. What would it be like to go through one? Picture drifting towards a black hole, but instead of finding a crushing singularity inside, you find a tunnel of light, or perhaps darkness, that somehow bypasses normal distances. Entering the wormhole might be a surreal experience. Space could stretch and tilt in strange ways, and moments later you might find yourself in a completely different place, maybe on the other side of the galaxy, or in another galaxy altogether. The journey might be short for you, even instantaneous, while outside, others would see you disappear into one black hole, and then perhaps emerge from a different black hole-like object elsewhere. It's often thought that if wormholes connect two regions of our universe, the other end would resemble a white hole, essentially a black hole running in reverse, where things come out, but nothing can go in. The mouth of a wormhole might look much like a black hole's event horizon from the outside, except if you looked closely, you might catch strange light patterns indicating that light from some faraway region is exiting. On entry, instead of being trapped, you would feel a path forward that leads you out. While this sounds like a sci-fi dream for interstellar travel, nearly all analyses agree that forming a traversable wormhole and keeping it open would be incredibly challenging, if possible at all. Still, the concept captures our imagination. Perhaps somewhere in the cosmos natural wormholes exist, maybe microscopic ones flitting in and out of existence in the quantum foam of space-time, or ancient cosmic wormholes left over from the Big Bang, connecting parts of the universe or different universes. No evidence for wormholes has been found, but scientists have proposed clever experiments to search for signs, such as peculiar gravitational lensing events, or particles appearing seemingly from nowhere, which might hint at something coming through a wormhole. As a mental exercise, though, wormholes allow us to wonder about connections that a black hole might have. Rather than an ultimate dead end, a black hole could in theory be half of a couple, the entrance, while a white hole, or another black hole elsewhere, serves as an exit. If one were to approach a rotating black hole, which has a different internal structure mathematically from a non-rotating one, equations actually suggest there could be paths that miss the singularity and pop out into another region of space-time. Those paths, however, would likely be highly unstable if any disturbance or realistic condition is introduced. In our relaxation journey, imagine drifting near the event horizon of a massive spinning black hole and somehow slipping through a hidden passage, a wormhole, instead of hitting the central singularity. One moment you're in one corner of the universe. A heartbeat later, you find yourself in a completely foreign sky. Perhaps the stars around you are unfamiliar, or you emerge in a quiet void between galaxies. or even an alternate universe with its own laws. The possibilities open up like a flower in the darkness. Such images remind us of how much remains unknown. Wormholes straddle the line between science and imagination. They have a foundation in serious physics, but have not been proven to exist. Nonetheless, they invite us to think big, to consider that the cosmos may have hidden doors and shortcuts, and that black holes, feared as destroyers, might also be portals to the beyond. Whether or not nature actually makes wormholes, the idea expands our minds and leads us perfectly into another related notion, that of white holes, the possible other side of a black hole's coin. White holes are something of a mathematical sibling to black holes. If a black hole is an object that nothing can escape from, a white hole is the opposite, an object that nothing can enter. In theory, a white hole would explosively eject matter and light, but you could never go through its event horizon from the outside. It only ever spits things out, never taking anything in. It's essentially a time-reversed black hole. The equations of general relativity in a vacuum are symmetric in time. If they allow a black hole solution, they also allow a white hole solution. However, whereas black holes can form from physical processes, like collapsing stars, we don't know of any process in nature that would lead to a white hole forming. A white hole, if one existed, might look like an extremely bright object, perhaps similar to a Big Bang on a smaller scale, spewing out energy and matter, then eventually diminishing. But once it's done, it would leave nothing behind, because by definition, a white hole would not let anything in to sustain it or interact further. One way white holes enter discussions is as the hypothetical exit of a wormhole. If a black hole's entrance leads through a tunnel, the exit might behave like a white hole. When you emerge, you cannot turn around and go back in through that side. Instead, that side might only allow you to go outwards. Some speculative cosmologies have even suggested that perhaps our own universe's birth, the Big Bang, was like a white hole, a burst of matter energy coming from a singularity, possibly connected to something like a black hole in another universe. This is a highly conjectural idea, but it shows the creative ways scientists try to understand the origin of things using these extreme concepts. Another place white holes appear is in extended solutions of rotating black holes, the Kerr solution, or charged black holes, Reissner-Nordström solution, where the mathematics shows multiple regions, including potential wormholes and white hole regions. In those idealized cases, one might enter a black hole, avoid the singularity, and come out of a white hole in a new region of space-time. But in reality, adding just a bit of disturbance or realistic matter tends to make those extensions collapse, meaning the white hole portion doesn't survive when you consider a real star collapse or any perturbation. If white holes do not exist in our universe, they remain a useful concept to think about symmetry and time's arrow. A black hole gradually takes in things and hides them. A white hole would hurl things out. If you were near a white hole, you would see matter and radiation streaming from an empty-looking point in space, like a fountain. But if you tried to approach that point, you'd encounter a barrier, the same kind of event horizon barrier, but from the opposite side. It would push you away with intense radiation and gravity, never allowing entry. For a moment, imagine witnessing a white hole. It might be a short-lived phenomenon, maybe appearing as a bright flash as it dumps out whatever was inside, if it had an inside region connected somewhere else. Perhaps it even could be mistaken for a supernova or gamma-ray burst if it were small scale. But then it would be gone, leaving emptiness. To date, we have not identified any definite white hole. Some astronomers speculated whether certain unexplained cosmic bursts could be mini white holes popping into existence and then vanishing, but nothing conclusive has been seen. Still, the concept of a white hole gives us a poetic completion to the idea of a black hole. Where the black hole is a sink, a white hole is a source. In our grand theme of beyond, white holes stand as a reminder that the universe might have counterparts and opposites beyond the ones we know. If a black hole in one universe leads to a white hole in another, then perhaps creation and destruction are two sides of the same cosmic coin. Matter lost in one place appears in another. It's a tantalizing notion that hints at a deeper interconnectedness, or at least at the surprising outcomes general relativity's equations allow when untethered from some constraints of reality. Whether wormholes or white holes exist or not, they serve as thought experiments stretching our imagination. As we ponder them, we naturally begin to question the uniqueness of our own universe's structure and the flow of time. Could black holes be gateways, not just in space, but to entirely different realms or eras? This brings us to the idea of alternate dimensions and time travel, which weave into the tapestry of black hole lore and speculation. The concept of alternate dimensions, beyond the three of space and one of time that we directly experience, often enters discussions of black holes and cosmology. Some advanced physical theories, like string theory, suggest there may be additional spatial dimensions that are normally hidden from us, or curled up at very small scales. If such dimensions exist, black holes could potentially interact with them in interesting ways. For example, one idea in higher dimensional theories is that gravity might spread out into those extra dimensions, which could change how black holes behave on small scales. There was even speculation that in high-energy collisions, like those in particle accelerators on Earth, if extra dimensions are present, tiny micro-black holes might form for an instant. These would be extremely small black holes, far smaller than an atom, popping into existence and then evaporating via Hawking radiation almost immediately. It was a theoretical possibility that captured imagination and even concern in the public sphere. Though calculations indicated that if it could happen, the black holes would vanish harmlessly. So far, no such micro-black holes have been observed in colliders, which puts constraints on those extra-dimensional models. In a universe with more dimensions, a black hole might look different. For instance, in 5 dimensions, instead of just spherical black holes, you could have something like a black ring or other exotic shapes as solutions. However, if these exist, they likely quickly settle into the most stable form or evaporate. The mathematics of higher dimensions is complex, but it shows us that black holes are a phenomenon not limited to our familiar 4D space-time. They can be conceived in various dimensional settings. Alternate dimensions could also provide routes for phenomena like wormholes. Some theories propose that what looks like a black hole in our 3D space might actually be a throat extending into a higher dimensional space. Think of a 2D surface like a sheet that has a deep well going down into a third dimension. A being living in 2D sees a circle, the hole's mouth, and cannot perceive the depth. Similarly, perhaps black holes are portals that extend into dimensions we can't directly see. That might allow something to bypass what seems like a singularity in our dimensions by traveling through a higher dimensional path. There's also the idea of brain worlds, where our universe is like a membrane, brain, in a higher dimensional space. In some brain scenarios, only gravity moves freely in all dimensions, while light and matter are stuck on our 3D brain. A black hole might then leak some of its gravitational influence off the brain. One could imagine that maybe Hawking radiation or some other effect could appear different if a black hole can radiate into invisible dimensions. We haven't seen evidence of such anomalies, but scientists do look for slight deviations in gravitational law at small scales, or astrophysical hints that could suggest extra-dimensional effects. When thinking of alternate dimensions in a more literary or imaginative sense, one might consider whether falling into a black hole could somehow eject you into a different dimension or parallel universe. While mainstream physics doesn't provide an easy mechanism for that, the coupling of black holes and the multiverse concept is a rich ground for imagination. Perhaps every black hole is a doorway to a new universe. As it pinches off from ours, it inflates into another realm where the mass and energy that fell in become the seed of a new cosmos. It's speculative and unproven, but it poetically addresses where all that stuff goes when it falls past the horizon. Maybe it's not lost at all, but rather continues existence elsewhere. Alternate dimensions and multiverse ideas remind us how limited our perspective can be. What we see as the whole universe could be just a slice of a far grander reality. Black holes, with their mysterious interiors, might be one of the few places where there's a connection to those larger realities, if such things exist. One bold hypothesis suggests a form of cosmic evolution. Perhaps each black hole births a new universe on the other side of its horizon. A universe that might have slightly different physical laws. In this view, universes that produce more black holes would spawn more new universes, a kind of natural selection on a cosmic scale, where the traits, physical constants, that lead to prolific black hole formation become more common in the multiverse. While highly speculative and untested, the idea is a fascinating attempt to answer why our universe has the properties it does. Maybe because such properties favour the creation of black holes, and thus, new universes. From the serene vantage point of our storytelling, we can imagine dimensions beyond the visible, layered like an invisible lattice around us. A black hole might create a funnel through those layers, twisting through an unseen direction. Should one travel that path, who knows where one might emerge? Perhaps in a parallel world, where time runs differently, or where physics takes a slightly different form. These ideas push the boundaries of our understanding and blend science with philosophy. It's breathtaking to consider that beyond the veil of a black hole's event horizon could lie not just the end of space as we know it, but a bridge to higher dimensions or new universes. Whether or not reality accommodates such extraordinary outcomes, exploring them in our minds brings a sense of wonder and opens our perspective on what beyond might truly mean. This segues into another enticing theme: time travel. Black holes warp time so drastically that they naturally invite speculation on travelling through time, forward or even backward. Could black holes, or other cosmic phenomena, allow us to move through time in non-traditional ways? Time travel is a concept that fires the human imagination, and black holes often feature in such discussions because of how they affect time. We've already touched on how a black hole can make someone experience time more slowly, a form of travel to the future, since you come out and more time has passed outside. But what about traveling to the past, or creating a loop in time? General relativity does allow some solutions that contain closed time-like curves, paths through space-time that return to their starting point in time, effectively loops that a traveller could follow to the past.
One of these solutions involves rotating black holes. The Kerr solution for a spinning black hole, if extended fully, and again ignoring the practical issue of stability, contains regions where time and space coordinates can become looped. In theory, a sufficiently fast rotation and an entry along the rotation axis might allow passage into another region of space-time, or even into one's own past. However, these scenarios usually require conditions like perfectly rigid structures or infinite-length objects, like infinitely long cylinders, and are plagued by instabilities or paradoxes. Nature seems to have ways to prevent paradoxical time travel. For instance, any tiny disturbance in a time-looping solution might destroy the loop or create a singularity that prevents completion of the loop. Cosmic strings, hypothetical ultra-thin and massively dense strands of energy left from the early universe, have also been proposed as a possible means to time travel, if two cosmic strings were to pass by each other at high speed, or one was travelling very fast. Some calculations suggest they could warp space-time enough to allow closed, time-like curves. Imagine two nearly parallel, infinitely long strings rushing by each other. Space and time would twist around them and, in principle, allow a carefully orchestrated trajectory that ends before it began. No one knows if cosmic strings exist. None have been detected so far. And even if they do, harnessing them for time travel would be an almost unthinkable engineering feat. Still, it's intriguing that our equations permit such strange possibilities. In the realm of black holes and wormholes, another time travel scenario emerges. If you had a traversable wormhole and you moved one end at high speed, or put it near a strong gravitational field, and then brought it back, you could create a time difference between the two ends. This is a bit like the twin paradox in relativity. One twin travels and comes back younger. If one mouth of the wormhole experiences less time, e.g. by being near a black hole or moving fast, than the other, then when you go through the wormhole, you could exit not only at a different location, but at a different time. Potentially, one could then travel into the past, relative to where they started, by going through the wormhole one way and then travelling normally back. This idea was explored by physicists like Kip Thorne in the 1990s as a thought experiment. They found that quantum effects would likely conspire to destroy the wormhole the moment it could act as a time machine, preserving causality. The universe, as far as we can tell, has a kind of built-in safeguard against time paradoxes, or at least it doesn't easily allow them. Still, the fact that our best theories come so close to permitting time travel is in itself astonishing. It suggests that time, like space, is flexible under extreme conditions, and perhaps under the right circumstances, the line between past and future could blur. For a gentle thought journey, consider the philosophical aspect. Black holes already unite space and time by warping them together. If one could circle a massive object enough or thread through a wormhole, might you catch glimpses of yesterday or tomorrow? In sci-fi scenarios, someone might orbit a black hole and come out finding they've gone back a day. Or a message sent through a wormhole might be received before it was sent. These scenarios are paradoxical and likely unrealizable, but they fuel the imagination and help physicists test the consistency of physical laws. What time travel ideas teach us in the context of black holes is that time and space are part of one fabric, and gravity, especially in extreme forms like black holes or cosmic strings, can stretch and twist that fabric into extraordinary shapes. Whether or not we can ride those twists to visit the past
we've learned that time is not absolute. Black holes are time machines to the future, via dilation, and they hint at more exotic possibilities that remain just out of reach. Pondering time travel also brings a certain reflective mood. It makes us question cause and effect, and consider the wholeness of time, our past, present, and future, all woven together in ways we barely perceive. Black holes, sitting silent and dark, might quietly be influencing the flow of time around them, like deep eddies in a river, creating whirlpools that mix what's upstream and downstream. For now, we observe from the shore, aware of the currents, but unable to plunge in without being carried away. Before we move on, let's shine a gentle light on cosmic strings themselves, those strange hypothetical objects we mentioned. Cosmic strings are not related to string theory's tiny strings. Rather, they are envisioned as massive, thread-like defects in the fabric of space-time, potentially formed in the very early universe when it was cooling from the hot Big Bang, somewhat like cracks that form as ice freezes. If they exist, a cosmic string could be incredibly long, possibly stretching across galaxies, but extremely thin, much thinner than an atom. Despite their narrowness, they would be immensely dense. A piece of cosmic string a mile long might weigh as much as the entire Earth, for example. What would a cosmic string do? Its gravity would be unusual, because a string isn't like a point mass or a sphere. It's an infinitely thin line, or a very large loop. Space around it would be heavily curved in a peculiar way. If you walked around a cosmic string, the geometry could be altered such that you might find that walking a full circle around it is less than 360 degrees. Space itself is conically shaped around the string. This means cosmic strings could cause strange lensing effects. A star or galaxy behind a cosmic string could appear as two identical images on either side of the string. As the light splits and goes around the string in different ways, cosmic strings, if oscillating or interacting, could also produce gravitational waves. If two cosmic strings cross and reconnect, they might create loops that vibrate and slowly lose energy via gravitational radiation, perhaps even evaporating eventually. Scientists have searched for the telltale signatures of cosmic strings, like double images of distant quasars or specific gravitational wave patterns, but none have been confirmed so far. It remains a possibility, but one that is growing more speculative as we don't see clear evidence. Still, they are fascinating to contemplate. Unlike black holes, which are points of infinite density, cosmic strings would be one-dimensional objects of high density. In some sense, they'd be like space-time floors stretching out. Some cosmologists describe them as remnants of phase transitions in the early universe, akin to cracks that form when water freezes into ice, except the water is the field that fills the universe. If one were to encounter a cosmic string, what would it look like? Likely invisible directly, since it emits no light, but we might see its effects. Perhaps a background of stars might appear oddly duplicated or shifted. If it passed through a planetary system, the orbits of planets would change slightly due to the altered geometry. Getting very close to one would be dangerous due to tidal gravitational forces. Although not as intensely deadly as a black hole's singularity, because a string's gravity, while strong, is distributed along its length. We earlier mused how cosmic strings might even allow time loops if configured just right. This hints at their extreme gravitational influence. But even if they don't enable time travel, they would rank among the strangest structures in the cosmos. literal threads of space-time tens of thousands of light-years long, whipping through the universe. In the serene context of our journey, cosmic strings add another texture to the cosmic tapestry. They remind us that the universe's potential oddities aren't limited to spheres and holes. There could be cosmic filaments of incredible mass sewing through space. So far, they remain theoretical, but the quest to either find them or rule them out continues. And in doing so, we learn more about how the universe evolved in its infancy. Having wandered through wormholes, white holes, extra dimensions, and time loops, we can turn back to a more concrete plane for a moment. The idea of simulating and exploring these phenomena from the safety of distance or theory, and how perhaps future beings might leverage black holes for their own purposes. Since we cannot practically travel into a black hole or witness these extreme conditions directly, scientists rely on simulations, both mathematical and computer models, to explore these realms. Modern astrophysicists use powerful supercomputers to simulate the conditions around black holes and the dynamics of space-time. They set up virtual universes with the equations of general relativity and see what happens, for example, when two black holes merge, or when a star is torn apart by a black hole's tides, or how accretion disks behave and produce jets. These simulations produce rich data. They can show us gravitational wave signals, flashes of light, or how magnetic fields twist, all based on physics equations. The results help us interpret real observations. For instance, long before we imaged a black hole or detected gravitational waves, we simulated what those phenomena should look like. When observations matched the simulations, it was a strong confirmation that we understand at least the basics of what's going on. One famous simulation was of the black hole image itself. Decades ago, scientists like Jean-Pierre Luminet and others simulated what a black hole surrounded by glowing gas would look like to an observer. They produced a ring-like image with a dark center, strikingly similar to what was eventually observed with the Event Horizon Telescope. Similarly, simulations of neutron star or black hole collisions predicted the gravitational wave chirps that LIGO would find. It's a triumph of human imagination and computational power that we can in some sense see these events in our mind's eye using mathematics, long before our instruments catch up. Simulated spacetimes aren't just limited to computers. Physicists have devised laboratory analogues of black holes to test certain predictions. For example, to test Hawking's ideas, researchers have created something called a sonic black hole in ultra-cold atomic systems. In these, sound waves play the role of light. They flow through a medium that is moving faster than the speed of sound in some region, creating a horizon for sound, analogous to an event horizon, since sound cannot escape from the region where the flow exceeds its speed. Amazingly, in such setups, they have observed effects similar to Hawking radiation, with phonons, quantized sound waves, being emitted in pairs, one inside and one outside the sonic horizon. Of course, this is an analogy, not a real black hole, but it provides a way to experimentally probe the concepts in a controlled setting. Another analog experiment uses optics. Scientists have made analog event horizons using light in nonlinear fibers, where a moving refractive index change can trap light akin to how gravity traps light in a black hole. These creative experiments let us study aspects of black hole physics like horizons and Hawking radiation on a tabletop.
It's mind-bending to think a process we usually associate with massive astrophysical objects might be mimicked with fluids, lasers, or other laboratory systems. By simulating spacetimes, whether with computer calculations or clever physical analogues, we gain confidence in our understanding. We also train our intuition for these strange realms. The imagery and data from simulations feed into our meditative visualization. When we describe what it might look like near a black hole or inside a wormhole, we're partly guided by what these theoretical explorations suggest. We can imagine it more vividly because scientists have charted those waters mathematically. One can picture a team of scientists watching a supercomputer animation of two black holes merging, seeing the ripples propagate in a visualization of space-time, or watching a render of a spinning disk around a black hole producing jets. These are like virtual voyages, not unlike the mental voyage we're on, bridging the gap between equations and experience. In a philosophical sense, our ability to simulate these exotic places shows how interconnected our minds are with the cosmos. Using logic and creativity, we extend our senses to places we cannot physically reach. It's a quiet triumph of human curiosity and patience. Through simulation, we have, in a sense, visited black holes in the theatre of the mind and confirmed their existence and properties through later observation. It's a wonderful synergy, thought guiding observation and observation refining thought. Yet for all the simulations, nothing replaces the awe of the real thing. We may never stand at the edge of a black hole with our own eyes, but each piece of data and each simulation is like another brushstroke in the painting of our cosmic understanding. It allows us to dream a little more clearly about these distant, shadowy giants. And as we dream, we can't help but wonder, might there come a time when intelligent beings, perhaps humanity in the far future, or some other civilization, engage with black holes, not just from afar or in simulation, but directly? The thought of directly interacting with black holes brings us to the realm of advanced civilizations and future exploration. Black holes, being powerful sources of gravity and energy, could in theory be both peril and promise for a sufficiently advanced technology. One can imagine a civilization that has learned to live in harmony with these dark giants, or even to exploit their extreme properties for practical purposes. Consider energy. Black holes, especially ones with accretion disks or ones that are evaporating, can provide energy. An advanced civilization might construct a megastructure around a black hole to collect energy from its accretion disk or jets. Some theorists have proposed the idea of a Dyson sphere, not around a star, but around a black hole. If the black hole has a steady stream of infalling matter, like gas from a companion star, the radiation from the hot disk could be captured by orbiting collectors. Even the Hawking radiation of a smaller black hole could be a power source, if one could create or obtain a small black hole, perhaps a few billion tons mass, which would radiate significantly. In fact, Hawking himself speculated about advanced beings using black holes. A black hole of about a mountain's mass would emit roughly as much power as a large power plant through Hawking radiation. Another possibility is using a spinning black hole as a kind of energy extractor through what's known as the Penrose process. In the ergosphere of a rotating black hole, a region outside the event horizon where space-time is dragged along by the rotation, it is possible, theoretically, to send in a particle and have some of its energy extracted, coming out with more energy than it went in, while the black hole loses some rotational energy. An advanced civilization might drop masses into the black hole in carefully planned orbits,
to slow the black hole's spin and extract energy, effectively mining rotational energy. This is a fantastically advanced concept, but it shows that black holes hold vast reservoirs of energy that, in principle, could be tapped. Beyond energy, a civilization might use black holes for computation. There are speculative ideas about using the intense gravity to perform hyperfast computations or as quantum reservoirs. Some even imagine that inside black holes or on their event horizons, vast computational matrices could exist, perhaps even giving a science fiction basis for thinking about black holes as possible habitats for very exotic life or AI, though this is extremely speculative. Black holes could also be used for travel in indirect ways. A starship might slingshot around a black hole to gain speed, similar to how we use planetary gravity assists, but on a more extreme scale, allowing it to reach distant stars more quickly. The time dilation effect could be used intentionally. For example, a ship could orbit close to a black hole for a while if they wanted to see far into the future when they come out. Effectively a time vault scenario where they can skip forward years or centuries outside while experiencing little time themselves. Though one would wonder, why do that unless they had a specific reason? On a darker note, one might consider using black holes as ultimate waste disposal, or even as weapons, in a very theoretical scenario. Dropping dangerous waste into a black hole hides it almost perfectly, aside from subtle changes in mass and radiation. And some sci-fi stories have imagined creating an artificial micro-black hole and sending it to an enemy planet, letting it consume or disrupt the planet. An extremely risky and morally fraught concept, needless to say. If there were a civilization living near a black hole, perhaps on a planet orbiting a black hole, like a rogue planet captured by a black hole's gravity, or a planet around a black hole that has a disk providing light, their experience of the universe would be quite unique. They might see strange sky distortions from gravitational lensing, and their time relative to the rest of the galaxy would be slowed. If they attempted to communicate with the outside, they'd see external events happening faster, and outsiders would see them moving in slow motion. Consider the sky from that world. It might be mostly black, no rising or setting sun to mark days if the planet is not near a star. Instead, a softly luminous ring could hang in the sky, the accretion disk of the black hole, or perhaps distant starlight bent into a halo. The black hole itself might appear as a circular void, maybe visible only by the absence of stars or a dim corona of light around its silhouette. If the black hole is actively accreting, the sky could be bathed in a faint, eerie glow from the disk, or occasional flares when matter falls in. Perhaps the planet's surface is illuminated by this ghostly light, casting subtle shadows. On the horizon, one might see the starlight from the rest of the galaxy warped and stretched as it passes near the black hole. The familiar constellations, if any were recognizable to them, would distort when rising or setting near that zone of strong gravity, creating a nightly spectacle of shifting patterns. Timekeeping for such inhabitants would be tricky. Mechanical clocks would tick normally locally, but if they ever compared them to clocks far away, they'd find discrepancies. They might even observe something peculiar. If a distant supernova erupted, or a star changed brightness in the wider galaxy, it could appear to evolve quicker in their sky than expected, because their whole world's time runs slow from an outside perspective. The culture of such beings, if they exist, would surely revolve around the black hole's presence. They might have myths or scientific theories about the great darkness in the sky. Maybe they view the halo of light around it as a divine sign or a cosmic gateway. Perhaps they have long realized that entering too close to that void means never returning, and their lore speaks of it with reverence and caution. They may celebrate the strange, slow passage of time as a gift, allowing deep contemplation, or conversely, they might yearn to know what happens in the fast-paced universe outside. These imaginings give a personal context to the abstract physics. Life under the influence of a black hole would adapt to the peculiar environment. It underscores how diverse and surprising the universe can be. Somewhere, even the unlikeliest habitats might exist, turning what we see as a deadly region into someone's home, under a sky dominated by a beautiful, terrifying black hole. Imagining these possibilities, we get a sense of partnership with the cosmos. Intelligent life reaching out to dance with one of the universe's most fearsome creations. It's a dance of caution and respect. For one misstep near a black hole could be fatal, but in mastering such a dance, the rewards in knowledge and energy could be enormous. This line of thought brings a hopeful twist to our meditation. Even the darkest places in the universe might one day be havens of knowledge and progress. It suggests a future where the mysteries we now observe from afar could become places we visit, study up close, or even utilize. Having stretched our minds to consider civilizations harnessing black holes, we can now visualize a scenario of exploration. Perhaps a future expedition to a black hole, something that ties together much of what we've learned and speculated in a final vignette of our journey in part 1. Picture, if you will, a scene perhaps many centuries from now. A spacecraft approaches a black hole in serene silence. This is not a reckless plunge, but a carefully planned expedition. The craft holds its distance just outside the intense gravity well, orbiting in a safe trajectory. Our vantage point drifts alongside this ship, gazing out with the crew at the spectacle before them. They see a massive black sphere silhouetted against a backdrop of stars. Around it, a subtle ring of light shines, perhaps a faint accretion disk from wisps of gas the black hole is nibbling, or the distorted star field being lensed into a halo. The stars behind the black hole appear warped into a circular band of light encircling darkness. It is a sight both eerie and beautiful, a black sun hanging in space with a crown of bent starlight. The crew on board speaks in hushed tones, aware that outside their hull, time itself is flowing differently. They have atomic clocks synchronized with Earth. Each hour near the black hole might correspond to 2 hours back home, depending on how close they venture. They conduct experiments. Perhaps they release a probe towards the event horizon. We follow this probe as it descends, sending signals back until the signals stretch and fade. Instruments on the probe record gravitational forces, space-time curvature, maybe even attempt to measure Hawking radiation in the vicinity. The probe's transmission becomes slower and more red-shifted as it approaches the horizon, just as our earlier considerations predicted. Eventually, the signal becomes too weak and shifts out of detectable range. The probe crosses the point of no return, and the crew logs the data received until that final moment. For them, this is a successful mission. They've gathered information up to the very edge of a black hole. Perhaps they even attempt a daring maneuver, skimming the edge of the horizon with their spacecraft to test time dilation directly. With precise thrusters and autopilot, the ship dips closer for a calculated interval. The crew's voices and movements feel normal to them, but their colleagues on a distant mothership or station see the craft's time slow. after what seems like a short while to those near the black hole, they return to a higher orbit and re-establish contact, only to find that much more time has passed outside than they experienced. In effect, they've leapt forward into the future relative to their starting point. It was a planned leap, a one-way trip in time used as a tool to maybe see the outcome of some long-term experiment, or simply to demonstrate the reality of relativity. As they gaze into the black hole's darkness, one astronaut reflects on the profound nature of what they are seeing. That darkness contains everything that has fallen into it over eons. Secrets of long-gone stars. Maybe even planets locked away. It's like staring at eternity made manifest. The black hole itself gives no clue, no revelation of what it has seen. It just is, silent and unyielding. And yet, around it, the universe is lit up by its influence. The ring of light, the whirling of nearby stars, caught in its grip, the very trajectory of their spacecraft curving in space-time. The mission might deploy a network of satellites around the black hole to map the space-time curvature in detail, creating a 3D image of the gravitational well. They could drop hollow spheres or lasers to watch how they stretch, and whether any subtle vibrations, perhaps from gravitational waves or Hawking radiation, can be detected. Each experiment unfolds gradually, with the crew patiently observing and meditating on the nature of what they study. During the long orbits, the crew experiences calm moments of contemplation. From their unique vantage, the cosmos looks different. If the black hole is near a galactic center, perhaps they see the dense clusters of stars moving rapidly around an unseen center. A grand cosmic dance they've become part of. If it's a more isolated black hole, they might see mostly the emptiness of interstellar space, punctuated by the black hole and distant stars. In either case, they are aware of being at a frontier of human experience. Imagine the psychological and almost spiritual impact on these explorers. In the quiet of their ship, with instruments humming softly, they stare out at a phenomenon that for millennia was only theorized. Now it's in front of them, real and majestic. Perhaps one of them reads aloud from notes or memory the words of earlier scientists who predicted black holes. They realize they are living the fulfillment of those predictions and going beyond, touching the unknown. Maybe they have on board a small memorial or tribute, a plaque with the names of Einstein, Schwarzschild, Hawking and others, which they plan to leave in orbit as a symbolic gesture, honoring those who unveiled this mystery. They send a final probe, a tiny encapsulated library of humanity's knowledge, maybe even, fancifully, letting it fall into the black hole, not out of waste, but as a poetic act of sending our story into the abyss, like casting a message into the cosmic ocean. They know it will never emerge, but there's something poignant in giving something to the black hole, a thing that has only taken and never given. As the mission concludes, the spacecraft gently fires its engines, bidding farewell to the black hole. The crew watches the dark sphere recede, the distortion effects easing as distance grows. The stars behind it realign to their natural positions. The black hole becomes just another pinprick of darkness behind them. Perhaps they feel a tinge of sadness leaving this profound object, but also relief and gratitude. They have come close to one of nature's ultimate enigmas and returned to tell the tale. This speculative mission ties together all we have learned: the gravity, the light bending, the time dilation, the mystery of the unknown interior, and the human longing to touch the beyond. It's a quiet adventure. There's no dramatic Hollywood chaos, just careful movement and observation, fitting for a meditation. And in that quiet, the significance of the accomplishment speaks loudly. Now the ship and its crew set course for home, or maybe to the next cosmic destination. We too, in our journey of the mind, will leave this black hole's vicinity. But the impression it leaves on us will linger. The cosmos is dotted with these black holes, each a reminder of both the power and mystery of nature. As we drift away, we consider all that we have witnessed on this journey so far. And yet, there are still more wonders to explore, more questions to ponder in the vast expanse of space and time. Our journey is not over. Many chapters remain in this cosmic odyssey, waiting calmly just beyond the next horizon. Up to now, we have explored what a black hole is. The way a star's collapse can curve space-time into a deep well. The point of no return at the event horizon. And even humanity's first glimpse of a real black hole's shadow. That eerie halo of light surrounding darkness in a distant galaxy's core. We've learned how black holes influence their surroundings, how they can power quasars and warp light itself. All of these insights were breathtaking and set the foundation. Now, we voyage further into the unknown, into questions that scientists are still puzzling over, and ideas that push the boundaries of our understanding. Yet behind that veil of darkness lies a paradox that has puzzled scientists for decades. For all we have learned about black holes, these mysterious cosmic entities still guard many of their secrets. In the quiet of space, a black hole appears deceptively simple. A dark sphere of nothingness, silently swallowing any light or matter that strays too close. In earlier times, black holes were considered almost mythical. Even Einstein initially suspected nature might avoid such infinities. But over the decades, evidence for these dark entities grew, from stars whipping around invisible heavy centers to exotic X-ray flashes from galactic cores, until their reality could not be denied. Still, an unsettling question remains. Imagine tossing a message in a bottle into the ocean. You might never retrieve it, but you trust that somewhere, in principle, that bottle still exists with its message. Now imagine tossing a physical object, say, a book or even a person, into a black hole. To an outside observer, it seems gone forever, beyond the event horizon from which no information can return. But is the information truly lost from reality itself? Or is it somehow preserved in ways we cannot yet see? This is the black hole information paradox, and it strikes at the heart of our understanding of physics. To grasp why this paradox is so profound, we need to remember how black holes bend the normal rules of the universe. According to Einstein's theory of general relativity, a black hole is an extreme warp of space-time, from which nothing can escape once it has crossed the event horizon. It's as if space itself falls inward, carrying everything with it. If you were to fall in, all traces of you would seem to vanish from the outside perspective. However, quantum physics, the laws governing the tiniest particles, insists that information cannot simply vanish. In the quantum world, if you know the present state of something perfectly, you can in principle reconstruct its past. Every process, no matter how chaotic, can be reversed. Nothing is lost, only transformed. These two truths, general relativity's prediction of complete disappearance and quantum theory's insistence on preserving information,
come into direct conflict at a black hole's edge.
In the 1970s, the renowned physicist Stephen Hawking made a startling discovery that sharpened this paradox. By applying quantum theory to the curved space-time around a black hole, he found that black holes aren't entirely black. They emit a faint glow of particles and energy, now known as Hawking radiation. Over immense timescales, this radiation will cause a black hole to evaporate, slowly shrinking it until, eventually, it could disappear entirely.
Hawking showed that this radiation is almost completely random, carrying away essentially no detailed information about what fell into the black hole. Only the most basic attributes, mass, electric charge, and spin, seem to influence the outgoing glow. The rich details of whatever formed the black hole, or whatever it has devoured, whether it was a star, a planet, or a library of books, appear to be washed away. If the black hole evaporates fully, all that detailed information would seemingly be gone from the universe, erased as if it never existed. This is the essence of the information paradox. Does a black hole's evaporation truly destroy information, defying the usual laws of quantum physics? Or is there some hidden mechanism by which the information is preserved and released? For a long time, Hawking himself argued that the information was indeed lost, that black holes break the usual rules, and that perhaps quantum theory would need to bend. This bold claim disturbed many physicists because it threatened one of the bedrock principles of physics, that information is never truly destroyed. If black holes could make the universe forget its own history, the logical threads connecting cause and effect would fray. Many scientists refused to accept that fate. They believed that somehow black holes must subtly store or release information to keep the cosmic ledger balanced. We just had to figure out how. Over the years, a number of intriguing ideas have emerged, each like a tiny beacon of light illuminating the darkness of a black hole's mystery. We will explore these ideas, letting them guide us further into the enigmatic heart of the black hole, and perhaps beyond. One clue to this mystery emerged even before Hawking's revelation of black hole radiation. Physicists noticed an intriguing parallel. The behavior of black holes seemed to echo the laws of thermodynamics, the science of heat and entropy. Entropy is often described as a measure of disorder or the amount of hidden information in a system. The second law of thermodynamics says that in any natural process, the total entropy, the disorder, tends to increase, or at least stay the same, in an isolated system. In the early 1970s, researchers studying black holes found that the area of a black hole's event horizon, the spherical surface marking the point of no return, also never decreases, much like entropy. If two black holes merge, the combined horizon area is greater than or equal to the sum of the areas before. This hinted at a deep connection. Perhaps the area of a black hole is itself a measure of entropy. In fact, the analogy runs so deep that the laws describing black hole behavior mirror the laws of thermodynamics 1-to-1. The event horizon's area behaves like entropy, and a black hole's surface gravity acts like temperature. Such parallels suggested a black hole might truly have a physical entropy and temperature, not just an analogy. This idea was proposed by a young physicist named Jacob Bekenstein. He boldly suggested that a black hole has an enormous entropy proportional to its horizon's surface area. In essence, he imagined that every tiny bit of the event horizon, every square Planck-length patch, a Planck length is an almost unimaginably small unit, could hold one bit of information. The more area, the more information capacity.
Initially, this was startling and controversial. How could a featureless black hole, defined by only a few properties, carry so much information? Physicists even coined the phrase, "black holes have no hair," to express how free of detail they seemed beyond mass, spin, and charge. But if Bekenstein was correct, then black holes actually have a kind of hidden hair, a vast tangle of microscopic degrees of freedom encoded somehow on that horizon. Soon, Hawking's calculations provided strong support for Bekenstein's idea. If black holes radiate like a warm object with a certain temperature, as Hawking found, then by the fundamental relationship between temperature and entropy, they must have an entropy. And indeed, the entropy Hawking calculated turned out to be proportional to the horizon area, just as Bekenstein had conjectured. This was a profound realization. A black hole, which looks from the outside like one of the simplest objects in the universe, actually harbors a vast number of microscopic states, hidden details that account for that entropy. It's as if the black hole's surface is covered in fine writing, an encyclopedia of everything that has fallen in, written in a code we don't yet understand. The information paradox then becomes even more tantalizing. Instead of a blank oblivion, a black hole might be more like a locked chest brimming with information. The question is not whether the information exists, but how it might escape or be revealed. One possibility is that Hawking radiation is not truly random after all. Perhaps it only appears random because we haven't deciphered its subtle encoding. It could be that the radiation is like a stream of scrambled signals, carrying away the data of everything that fell in, but in a form so thoroughly mixed and encrypted that to us it looks like mere noise. Over the lifetime of a black hole, countless eons of slow evaporation, this trickle of encoded information would, in principle, carry out every last bit of the story of whatever fell inside. From the perspective of our grand cosmic library, it would mean the books tossed into the fireplace were not destroyed after all. Instead, the information in their pages was gradually carried out by the smoke, just in shredded and scattered form. If one had a perfect understanding of all the physics and collected all the Hawking radiation, one could, at least in theory, reconstruct the original pages. Another possibility is that the information never truly leaves the black hole's vicinity in the first place, at least not in any conventional way. Perhaps it stays imprinted on the event horizon itself, like a memory etched into the fabric of space-time. Some researchers have likened the event horizon to a holographic screen, where the three-dimensional information of anything that falls in gets stored on a two-dimensional surface. In this view, the black hole's horizon is an illusion of emptiness. It's actually teeming with the quantum information of all that has ever crossed it. The interior of the black hole, in a sense, could be a projection of that information. If this is true, then there is no paradox at all. Information isn't destroyed, it's just hidden behind a veil, encoded on the horizon, and slowly released in radiation, or perhaps revealed if the black hole ever shrinks away. In a related vein, an idea called black hole complementarity suggests that from an outside observer's perspective, information never actually passes through the horizon at all. It gets hung up and smeared on that surface. Whereas from the perspective of someone falling in, they experience crossing the horizon normally and can't tell any information is stuck. Each perspective is self-consistent, and no single observer sees a violation of physics. Nature, in effect, tells two complementary stories that never directly contradict each other, ensuring information is preserved without allowing any one vantage point to witness
its complete journey.
There are yet more imaginative proposals. Some have suggested that a black hole might not evaporate away completely to nothing, but instead leave behind a tiny, stable remnant, like the burnt charcoal after a fire, that still contains all the information that fell in. Such a remnant might be incredibly small and nearly invisible to the outside world, but it would serve as nature's vault, safeguarding the information eternally.
Others propose that perhaps the information does leave our observable universe, but not by being destroyed. Instead, it could tunnel or slip into a new baby universe that forms within the black hole. In that scenario, what falls into a black hole isn't lost, it's just transferred. Our universe's loss is another universe's gain. From our side, we can never retrieve that information, making it effectively lost to us. But in the grand scheme of a multiverse, the story continues elsewhere.
Each of these ideas, information slowly leaking out, being stored on the horizon, lingering in a remnant, or escaping to a new universe, or some combination thereof, represents a bold attempt to resolve the paradox. The truth might encompass aspects of several of them. Today, many physicists believe, inspired by a principle called holography, that information is indeed preserved and can be recovered, at least in principle, from black holes. In time, as our mathematics and physical intuition sharpen, we suspect the paradox will be resolved in a way that does not require cosmic information to vanish. Instead, black holes will likely be understood as transformation engines, places where information is scrambled and reissued in new forms, but never truly lost. To see how this could be possible, we must dive deeper into that idea of the black hole's event horizon as a storehouse of information, as a hologram. In doing so, we find ourselves stepping beyond the confines of the black hole itself and into a revolutionary way of thinking about the universe as a whole. The notion that a surface can hold the full information of a volume isn't just a quirky feature of black holes. It may be a fundamental property of reality. This is the holographic principle, and it suggests that what we perceive as three-dimensional space might, at its deepest level, be a kind of projection from a two-dimensional boundary. It is as if the universe we live in is painted on the walls of an invisible cosmic room. This idea, initially inspired by black hole physics, was refined in the realm of string theory and high-energy physics. Physicists Leonard Susskind and Gerard T. Hooft were among those who conjectured in the 1990s that black holes were telling us something fundamental, that nature's ultimate storage of information happens on surfaces, not in volumes. A few years later, a precise example of this principle was discovered, a mathematical equivalence, or duality, between two very different kinds of theoretical descriptions. On one side was a universe with gravity in it, a model of space that had an edge or boundary. On the other side was a description defined only on that boundary, with one fewer spatial dimension, and with no gravity, something more like a quantum field theory. To everyone's astonishment, these two very different descriptions turned out to be completely equivalent, like two languages telling the same story. This was the first concrete realization of a holographic universe, often called the ADSL-CFT correspondence by experts, and it gave substantial credibility to the holographic principle. What does this mean in a more intuitive sense? Imagine that everything inside a region of space, including stars, planets, people, and yes, black holes, is somehow encoded as information on the boundary of that region. If you were a supreme being who could read that boundary, you would know exactly what is happening inside, down to every detail. In our everyday life, we don't notice this because we're living inside the hologram. Much like characters painted inside a vast mural might not realize their world is actually a flat canvas. But the mathematics suggests that the information content of a volume of space might really be determined by the surface area that encloses it. This strange outcome resolves the information paradox elegantly. The lost information was never lost at all. It was all along residing on the black hole's event horizon surface, and by extension, on whatever boundary the universe as a whole might have. And the Hawking radiation gradually carries it back out in a way consistent with quantum theory. The interior of the black hole, then, is not an independent realm where information vanishes, but rather part of a holistic system where information has multiple representations. This shift in understanding was so persuasive that in 2004, Stephen Hawking conceded a famous bet on the issue, acknowledging that information is probably preserved after all. In a playful ceremony, he presented fellow physicist John Preskill with an encyclopedia of baseball statistics, Hawking's way of symbolically returning information once thought lost. The paradox was far from solved in detail, but consensus was growing that a solution consistent with quantum physics exists, thanks in large part to insights from the holographic principle. This viewpoint drastically changes how we think about space and reality. It suggests that our familiar three dimensions might be more of an emergent phenomenon, a kind of effective description that comes from underlying information encoded in fewer dimensions. To use a metaphor, think of a woven tapestry. From afar, you see a continuous image on the fabric, maybe a detailed scene, but up close, you realize it's made of interlaced threads and knots. In one perspective, you have a picture. In another, you have a grid of threads. Likewise, our universe's space and time might be the picture, while the threads are quantum bits of information entangled with each other in a lower dimensional framework. These threads of the cosmic tapestry could be thought of as quantum entanglement linking bits of information. Entanglement is the mysterious connection between particles that can make them act in unison even across great distances. Many physicists now suspect that these connections are what literally stitch space together. If the entanglement between two regions of space is removed, it's as if the thread connecting them in the tapestry is cut. Those regions of space might drift apart or even become distinct, unconnected universes with a gap in between. This idea has led to a breathtaking conjecture that the fabric of space-time is essentially woven from quantum entanglement. Black holes fit into this picture as places where the fabric is extremely warped, and the usual threads of entanglement undergo radical rearrangement. When a black hole emits Hawking radiation, for example, pairs of particles are created at the horizon. These pairs are entangled with each other. One falls in, the other escapes. The escaping particle carries away some information. Its twin inside remains, but they stay connected by entanglement. Some physicists, in a whimsical yet profound suggestion, have even proposed that this entanglement could be viewed as a tiny wormhole, a hypothetical tunnel in space-time between the interior of the black hole and the outgoing radiation. In other words, the particle that escapes is not truly disconnected from the black hole at all. It's tethered by a quantum thread, a filament of space-time stretching out. Through these myriad entangled links, the black hole and its environment remain part of a single quantum system. Eventually, as the black hole evaporates completely, what was inside is effectively carried outside via these connections. Whether or not literal wormholes are the correct picture, the underlying message is that the separation between a black hole's interior and the outside world may be more of an illusion than we thought. The holographic principle and the entanglement connections suggest that everything is deeply interconnected. The interior of a black hole could be just another facet of the same reality described by particles and fields outside the black hole. This duality of inside and outside, of surface and volume, ensures that information is never truly trapped beyond redemption. Instead, it is stored and eventually broadcast in subtle ways through the language of quantum physics. As dreamy and abstract as the holographic idea sounds, it points toward a future where the concepts of here and there, inside and outside, blur at the fundamental level. Space and time themselves might not be the absolute, unbreakable stage we once thought, but rather flexible constructs arising from something deeper, something woven from information and relationships. Standing at the event horizon of this insight, we gaze outward and inward and see that black holes are not just holes in space. They are keys to deciphering the code that space and time are written in. Our journey now carries us into the realm of the ultra-small and ultra-dense, where space, time, quantum mechanics, and gravity all converge. This is where physicists seek a unified theory of quantum gravity, and where ideas like the holographic principle will be tested. It's also where even stranger possibilities about black holes emerge, ideas that challenge our imagination. Could the very singularity at a black hole's core be something radically different from a point of infinite density? Could quantum gravity reveal new structures, or even pathways to other universes? The next steps of our journey venture into these speculative territories, guided by the quest to unify the laws that rule the cosmos. In the quest to truly understand black holes, scientists have realized we need a framework that unites the cosmic gravity of Einstein with the quantum rules that govern atoms and particles. This hoped-for synthesis is often called a theory of quantum gravity. Black holes are the ultimate testing ground for such a theory, because within a black hole, gravity is immensely strong and quantum effects cannot be ignored. At the center of a black hole, classical physics predicts a singularity, a point of infinite density and zero volume, where known laws break down entirely. Time and space as we know them seem to end there, but infinities in physics are usually a sign that our theory has been pushed beyond its limits. Most physicists believe that in a true theory of quantum gravity, this singularity would be replaced by something finite and understandable, some new state of matter or geometry that doesn't destroy information. One leading candidate for a quantum theory of gravity is string theory. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy. These strings can vibrate in different modes to appear as different particles, and string theory requires extra dimensions of space beyond the three we experience, though these extra dimensions might be curled up too small for us to notice directly. When string theorists turned their attention to black holes in the 1990s, they made remarkable progress. They managed to model certain kinds of black holes, under very special simplified conditions, as collections of strings and brains, brain meaning a membrane-like object in string theory, and then count the number of possible quantum states of those objects. The number of quantum states essentially corresponds to the number of different microscopic configurations the black hole could have, which is a measure of its entropy. To their amazement and delight, the count matched exactly the Bekenstein-Hawking entropy formula for black holes. This was a major hint that string theory was on the right track. It provided a microscopic explanation for black hole entropy. In essence, it means that what we call a black hole might not be an inscrutable blob of nothingness at all, but instead could be understood as a vast ensemble of quantum states, a complex tangle of strings and brains vibrating and holding information. Building on this idea, some string theorists proposed the fuzzball concept. According to the fuzzball picture, a black hole has no traditional interior at all, no smooth, empty region leading to a singular point. Instead, the entire region inside what we call the event horizon would be filled with tangled strings and brains in all their possible forms, a seething quantum tangle that extends right up to the horizon itself. Up close, such an object wouldn't appear black or featureless at all, but rather like a hugely complex, exotic star made of quantum threads flickering and buzzing. Each possible arrangement of these strings corresponds to a different microstate of the black hole. From far away, all these microstates look identical. They all create the same gravitational pull and have the same outward appearance, the same mass, charge, spin, and a fuzzy surface at roughly the event horizon radius. But up close, in theory, they would be as diverse as different arrangements of matter inside a star, just incredibly compressed and exotic. The term fuzzball reflects that instead of a sharp boundary with an unknowable void inside, the black hole is like a fuzzy, packed ball of quantum stuff. In this view, when something falls toward a black hole, it doesn't hit a featureless horizon and disappear. It splats into this tangled yarn of strings, merging its information with the fuzz. The information it carries gets absorbed into the string's configuration. Over time, as the fuzzball radiates, which it can, since it's made of quantum constituents that can emit radiation, that radiation can carry away information about the state of the strings, thus allowing what fell in to be revealed eventually. The fuzzball proposal is one way string theory ensures that information isn't lost. There is no mysterious inside disconnected from the outside. Everything is encoded in the stringy structure that stretches to the horizon. While string theory provides one imaginative resolution, other approaches to quantum gravity offer different insights. Loop quantum gravity, for instance, suggests that space itself has an atomic or granular structure. A network of tiny loops, think of them as an extremely fine mesh of quantum threads, rather than a smooth fabric. In loop quantum gravity, the enormous densities inside a black hole might cause a drastic but orderly change. Instead of a singularity, the collapsing matter could reach a state of immense compression and then rebound, like a spring that has been pressed to its limit. This rebound might happen at a scale so small and over timescales so long that to an external observer, the black hole just appears to evaporate slowly via Hawking radiation. But from the perspective of the quantum geometry, that evaporation could eventually reveal a new phenomenon, a transformation of the black hole into something else, a white hole, perhaps, where the trapped contents are finally released in a grand expulsion. Some researchers have coined the term Planck star for a possible intermediate stage in this process, a black hole that compresses matter until quantum pressure of space-time itself halts the collapse. When densities reach the Planck scale, the smallest scales of physics, and then, after a very long time, pushes that matter energy back out. In this scenario, after an extremely long period, the black hole would effectively explode, spewing out the information it had consumed in one final burst of high-energy radiation, rather than quietly fading to nothing. It's a very different ending than Hawking's classical evaporation, but one that also preserves information. These ideas are speculative, and much work remains to merge the mathematics of quantum theory and gravity into a seamless whole, yet they instill a sense that the universe has clever ways to avoid the absolute destruction of information. Instead of a singularity that shreds reality, we might get a complex region where quantum laws still hold sway, finding avenues for information to persist or re-emerge. Whether it's strings vibrating in unison or space-time loops rebounding from collapse, the dreaded singularity could be replaced by something almost creative, a place where new structures form or where pathways to other realms become possible. Indeed, one of the tantalizing implications of quantum gravity is the possibility of bridges or tunnels in space-time, what we commonly call wormholes. If wormholes, which connect distant points in space and time, or baby universes can exist at all, it would likely be through quantum gravity effects that allow space-time to do things normally forbidden, like tear and reconnect. Some solutions in Einstein's general relativity equations already hint at the idea that a black hole could be connected to another region of space-time. For example, the idealized Einstein-Rosen bridge that mathematically connects a black hole to a white hole in another universe. Those classical solutions aren't physically realized in our universe, so far as we know. Real black holes form from collapsing stars, not from the pristine, eternal setup that those analytic solutions describe. But quantum gravity might allow something akin to that, an opening, or a birth of a new region of space-time when a black hole forms. This raises a thrilling question. Could black holes be gateways to new universes? As strange as it sounds, a number of thinkers have entertained this possibility, and it leads us to consider the nature of creation itself on the grandest scale. Our journey now turns to this speculative but awe-inspiring idea that in the death of a star, in the collapse that forms a black hole, there might be the genesis of a new cosmos hidden from our view. The notion that black holes might birth new universes takes us far beyond our usual cosmic horizons. It's a speculative bridge between the life cycle of stars and the generative processes of the cosmos itself. To grasp this idea, envision what happens as a massive star dies and collapses under its own weight. From the outside, we see the formation of a black hole, space folding in, a horizon forming, everything disappearing from view. But now imagine that deep inside that catastrophic collapse, as the core shrinks and densities soar, space-time doesn't simply crumple into a dead-end singularity. Instead, suppose it begins to stretch a new bubble of space, a bud that pinches off from our universe like a new branch from a tree. To any observer left behind outside, the black hole remains a black hole, an opaque sphere in our universe. Yet on the inside of that sphere, the bud might inflate, fueled by the immense energy of collapse, into an entire new universe. In that newborn cosmos, the point of detachment becomes its own Big Bang, an initial singularity from which space and time expand. The inhabitants of that baby universe, if any existed, would see a Big Bang origin, never suspecting that it was triggered by a parent universe's star imploding. This scenario is breathtaking. It suggests that every black hole could be a one-way portal to a new realm of existence. The information and material that fell in wouldn't be lost or destroyed. Rather, they would form the initial conditions and contents of a budding universe. From our side, once something crosses the horizon, it's gone. Indeed, nothing ever comes back out. For anyone dreaming of using a black hole as a portal to elsewhere in our universe, this is a caution. The journey doesn't loop back into our cosmos. Instead, the traveller and their ship would effectively leave our universe altogether, with no way back to report what they found. Black holes are one-way exits. the road leads out and does not return. But from the inside perspective of the new universe, that matter and energy are very much present, just taking on a new life in a new context. In this way, black holes would be cosmic seeds. Just as a seed buried in soil is hidden and dark, seemingly gone, yet can sprout into a vast tree, so too could a black hole's hidden interior blossom into a cosmos expansive and grand, though forever cut off from the parent universe that gave it birth. One thinker who has advanced this idea is physicist Lee Smolin. He proposed a hypothesis known as cosmological natural selection. In Smolin's vision, universes reproduce through black holes. Each new universe born of a black hole might have slightly different fundamental properties, different values for the physical constants, for example, much like a child might have genetic variations from its parents. These differences aren't random chaos, but small tweaks, as if some cosmic DNA gets copied with minor mutations. Smolin suggested that over many generations of universes, a kind of evolution could take place. Universes that happen to have laws and constants favouring the formation of lots of stars and black holes will produce more offspring universes, since each black hole is a potential baby universe. Those offspring universes inherit the traits, physical laws, of their parent, with slight variations. Over time, this natural selection could lead to universes increasingly fit to produce black holes. In other words, the reason our universe seems so hospitable to forming galaxies, stars, and black holes might be because it's the product of countless rounds of this cosmic selection. Less hospitable universes, ones with physical laws that, say, prevent stars from forming or cause them to burn out too quickly, would produce few or no black holes, and thus have fewer or no offspring. They'd be evolutionary dead ends. Assuming our universe is a typical member of this population of universes after many generations, it would be expected to be finely tuned to produce many black holes. This transforms black holes from devourers into creators, from final tombs to cosmic wombs. Each black hole could be a cradle of a new existence, a dark parent giving birth to a baby cosmos. It's a poetic inversion of their feared image, an agent of destruction that is simultaneously an agent of creation. This hypothesis even provides a kind of testable idea. If our universe's laws are the result of such cosmic natural selection, then those laws should be near optimal for producing black holes. Indeed, our universe does seem remarkably fruitful in forming long-lived stars, which end as black holes, and heavy elements, which allow planets and life, whereas many conceivable variations of physical constants might yield sterile expanses with few stars or black holes. In Smolin's view, that's no accident, but a sign that our cosmos has been selected for fecundity in black hole creation. While this idea is admittedly speculative and not confirmed by any evidence we can currently gather, it's fascinating because it offers a possible answer to an age-old question. Why do the fundamental constants of our universe, the strengths of forces, the masses of particles, etc., have the values they do? Those values seem oddly tuned to allow complexity and life. Cosmological natural selection suggests they are as they are because they've been honed by a cosmic evolutionary process that favours universes capable of generating complexity and abundant black holes. It casts black holes not as the ultimate dead ends, but as essential links in a chain of cosmic rebirth. Even without the evolutionary aspect, the raw idea of black holes birthing universes is profound. It implies a multi-layered reality. Our universe itself could have sprouted from a black hole in another universe, and within our universe, every black hole could contain its own realm with different physics. Picture a potentially infinite nesting of universes, like a cosmic tree with branches upon branches, black holes giving birth to new universes, which in turn eventually produce black holes of their own, and so on. Of course, this picture raises further questions. Could anything ever pass from one universe to another? Likely not, if the horizons are absolute one-way boundaries. The parent and child universes would be almost entirely cut off from each other. The parent sends matter information into the child as its initial content, but nothing comes back out to the parent except perhaps a subtle gravitational imprint before the whole formed. Observationally, from our universe's standpoint, this idea is hard to test. It remains more in the realm of philosophical cosmology than experiment. Just entertaining this possibility is mind-expanding. It suggests a universe far from static or singular. Instead, creation might be an ongoing process, happening unseen in the interiors of black holes all the time. The death of a massive star in one universe could be the birth of an entire cosmos in another branch of reality. It's a dramatic cycle of death and rebirth on a scale that dwarfs even the life cycles of stars. And it provides a powerful image of impermanence and renewal. Even the collapse into darkness can give rise to new light elsewhere. As we float in the thought of multiple universes and cosmic rebirths, it's worth noting how far black holes have taken us. From understanding simple gravity to the edge of metaphysics. We started with a paradox about information and ended up contemplating an endless fountain of universes. Black holes, in forcing us to confront their mysteries, act as gateways to grander ideas. Whether or not nature truly operates this way, the exercise broadens our perspective immensely. Now, stepping back into our own universe, we can ask a different sort of question. What if the strange properties of black holes are not just outlandish features of reality, but hints that reality itself might be something different than we thought? What if, for instance, our universe, with its black holes and quantum quirks, is some kind of cosmic experiment, or even a computation? In the same way we speculated about black holes being seeds of new universes, we might wonder about the context of our own cosmos. Could it be that black holes serve a role in a larger system, perhaps even a simulated one? We turn now to these more philosophical and futuristic musings, where black holes meet the idea of a programmed cosmos and the concept of information as the foundation of everything. We live in an age where the line between physics and information theory grows thin. Some thinkers have suggested that at its most fundamental level, the universe might be made of bits of information, and that everything we see is the result of cosmic computations. Physicist John Archibald Wheeler famously said, "It from bit," implying that every particle, it, emerges from information, bit. In this view, physical laws are like a program running on an underlying informational substrate. If one takes this idea to an extreme, it dovetails with the science fiction notion that perhaps our whole universe could be a simulation running on some unimaginable cosmic computer. Within such a simulation, black holes would be very curious objects indeed. Perhaps they could be seen as subroutines of the cosmic code, exotic data processing hubs, or even garbage disposal mechanisms for information. Think about what a black hole does. It takes in matter and information in a seemingly irreversible way, and eventually returns energy in a highly scrambled form, Hawking radiation. This is reminiscent of a computer algorithm that takes an input and produces an output that looks random. In cryptography and computing, there are functions that irreversibly scramble data, at least for practical purposes, thoroughly mixing it. Black holes might be nature's analogue, the ultimate scramblers. In fact, theoretical studies suggest black holes are fast scramblers of information, meaning they mix up information faster than any other known system in the universe. It's as if once something falls in, its identity is rapidly diffused among all the degrees of freedom of the black hole. From this perspective, a black hole could be thought of as a device that rapidly processes and hides information. One researcher, Seth Lloyd, once speculated about the ultimate laptop, a computer made by compressing matter so much that it forms a tiny black hole. He calculated how many computations such a black hole computer could perform. The numbers were astounding. A black hole, just a few centimeters across, could theoretically outperform any conceivable ordinary computer by staggering factors, running at the maximum speeds allowed by physics. The idea is that because black holes concentrate so much energy and have such high entropy, information capacity, they are natural maximizers of computational potential. All those internal configurations that account for a black hole's entropy could be seen as different memory states, and the dynamics of the black hole, as it evolves and radiates, could be viewed as a kind of computation. If the universe as a whole is performing some kind of computation to evolve from state to state, then black holes are like the ultra-efficient processors in this grand cosmic computer. Now, if our universe were actually a programmed simulation, one could playfully speculate on what role black holes might serve in it. Perhaps they are data sinks, places to put information that is no longer needed in the simulation, effectively sealing it off. Since no observer within our universe can retrieve what goes inside, the simulation might not need to fully calculate what happens past the event horizon, saving on computational resources, so to speak. To us inside the simulation, the physics up to the horizon is consistent and complete. But beyond the horizon, the program could have a lot of freedom, or might not run a detailed calculation at all. Maybe the simulation uses black holes as portals to transfer data between different parts of the program, or as cleanup routines to erase information in a controlled way. Of course, this is highly imaginative, a step more into philosophy than physics. But it highlights an interesting point. Because black holes hide information, they provide a kind of loophole in the transparency of physics. In a design system, such loopholes could even be intentional. On a less speculative note, even within known physics, black holes deeply influence the flow of matter and information in the universe. They shape the growth of galaxies through their gravity and sometimes through violent outbursts. For example, the supermassive black hole in a galaxy's center can gobble up gas and then expel some of it in powerful jets and winds, which in turn can heat or blow away gas in the galaxy, regulating the formation of new stars. Thus, black holes, though seemingly isolated, affect where and how structure forms. In that sense, they act as cosmic moderators of complexity. It's almost as if they are giant engines helping drive the evolution of galaxies, ensuring they don't form too many stars too quickly and burn out, or conversely, by merging and growing, helping to seed new activity in galaxy cores. Whether by cosmic design or natural law, black holes are woven into the story of our universe's information and structure. They challenge the notion of a predictable clockwork cosmos, where nothing ever truly disappears. Instead, they introduce mystery. Regions we cannot observe directly, outcomes we cannot know with certainty. In a way, they keep the cosmos partly hidden and open-ended, reminding onlookers like us that there's more to reality than meets the eye. Some philosophers of science say this mystery is essential. It hints that reality might have layers or levels of description we're only beginning to peel back. As we consider simulations and computations, we're essentially blurring the line between physics and philosophy, between experiment and experience. Even if the universe is not literally a computer program, thinking of it in terms of information processing provides powerful metaphors. It reminds us that black holes are not just astrophysical oddities, but also informational curiosities. They sit at the intersection of gravity, quantum mechanics, thermodynamics, and information theory, and any complete understanding of them forces us to unify these domains. Our journey has now touched on the scientific and the speculative, the physical and the philosophical. We explored how it, the material world, might arise from bit, information, how a universe might be a grand computation, and how black holes challenge our conventional distinctions.
Perhaps one day, far in the future, advanced intelligences might harness these ideas, using black holes as ultra-powerful quantum computers, or even creating simulated universes within them. In such a scenario, beings inside those simulated universes might look out at their black hole boundaries just as we do ours, pondering the mystery, unaware of the code running beneath. It's astonishing to consider. A fractal of universes within universes, information within information, a tapestry with no clear beginning or end.
All these lines of thought hint that information might truly be the bedrock of reality. The distinction between what is physical and what is information could be more a matter of perspective than fundamental. A rock, a planet, a person, each could be seen as a collection of information arranged in a particular way. Some have even speculated that consciousness itself arises from complex information processing, making it an intrinsic part of this cosmic computation. If the universe is indeed a kind of giant information system, then when we seek to understand it, it's almost as if the universe is striving to understand itself through us. This idea blurs the boundary between observer and observed, suggesting a deep unity between mind and cosmos. Across all these theories and speculations, a common theme emerges: impermanence and transformation. In the cosmic arena, nothing is truly static or eternal. Stars are born from clouds of dust, shine for eons, and then exhaust their fuel. To truly appreciate this impermanence, imagine watching the life of a star in time-lapse. A diffuse cloud of gas collapses and ignites into a newborn star. It burns brightly for millions of years. But in your accelerated vision, you see it swell into a red giant and then cast off its outer layers like a dandelion blowing in the wind. Perhaps its core collapses into a white dwarf that slowly cools. Or if it was massive enough, it implodes into a neutron star or a black hole. In mere moments of your imagined time-lapse, a stellar lifetime flashes by. Far from making the star's life seem trivial, this perspective highlights the cosmic artistry of change. From the star's remnants, new gas clouds will form, giving rise to the next generation of stars. Nothing truly disappears. It only changes form and continues the cosmic story in a new chapter. Many stars die in spectacular explosions, supernovae. Their ashes, enriched with new elements forged in their hot cores, scattered across space to seed new generations of stars and planets. Some of the most massive stars collapse into black holes at their end. Thus, Even in death, stars create the conditions for new life and new structures. The universe itself thrives on this continual recycling. It's like an endless series of seasons on a grand scale: creation, evolution, dissolution, and rebirth. Just as spring follows winter, bringing new life from the decay of the old, so the death of stars spreads the elements that will form new stars, new planets, maybe even new living beings. This cosmic impermanence might sound bleak at first. The idea that even the most enduring structures will one day fade. But there is profound beauty in it. It means the cosmos is alive with process and change. Just as seasons cycle or living beings undergo birth, growth, decay, and rebirth through their offspring or the return of their matter to the ecosystem, so too does the universe on grand scales. Nothing is truly lost in the sense of utterly vanishing without a trace. Instead, things change and reappear in new guises. The atoms in your body, for example, were forged in ancient stars that died long before Earth formed. Those stellar deaths allowed you to exist. In the same way, the dramatic fate of massive stars, collapsing to black holes or exploding and dispersing, sets the stage for the physics that shapes future galaxies or even future universes. Black holes thus embody both an end and a beginning. They even warp time itself in ways that boggle the mind. An outside observer would see clocks near a black hole tick ever more slowly compared to clocks far away. In essence, black holes are also time benders. It's conceivable that someone lingering just outside a black hole's horizon, in a sturdy spaceship, say, could experience only hours, while years or centuries pass in the outside universe. In theory, one could use this effect as a kind of time travel to the future. Hover near a black hole and then return to find civilization far evolved. This extreme time dilation is another reminder that our intuitions falter at cosmic scales. What feels like a long time to us could be an eye blink cosmically, and vice versa. By showing us that time can stretch and skew, black holes gently nudge us to appreciate the moments we have and the subjective nature of the flow of time. They also illustrate that endings can feed into new beginnings. Black holes are the tombs of stars, but maybe the wombs of new universes. They take the familiar and return the strange, yet perhaps what they return eventually becomes familiar again, given enough time or a different perspective. This viewpoint can instill a sense of cosmic humility. The dramas of our lives, the rise and fall of civilizations, even the life cycle of our own sun, a humble star that will, billions of years from now, swell into a red giant and then settle as a white dwarf. All these play out on the stage of a universe where change is the only constant. It's humbling to realize how temporary and small we are against the backdrop of stars exploding and black holes yawning open and evaporating over trillions of years. But at the same time, it's uplifting to realize we are part of that grand dance. The particles that make us have cycled through supernovas and perhaps even through black holes, only to become part of a thinking being, us, who can reflect on it all. Many philosophical and spiritual traditions have long embraced the idea of impermanence, that all compounded things must eventually change or fade. Black holes put a very stark face on that truth. They suggest that even knowledge and information must struggle against oblivion, yet they also hint that perhaps nothing of value is ever truly destroyed. only transformed beyond recognition. There's a parallel here with the human condition. We cannot hold on to moments. Time pulls us ever forward, and experiences slip into memory. But those experiences shape us, and in a way, they live on within us, much as information might live on in the universe, even after the events that created it have passed. The cosmos has its memory encoded in the fabric of space and the energy of radiation. We have ours in the connections of neurons in our brains. Both are vulnerable to decay, but both strive to preserve meaning. When thinking of cosmic cycles, one might recall ancient concepts of time. Hindu cosmology, for instance, speaks of vast cycles of creation and destruction. Yugas and kalpas, the days and nights of Brahma, that span trillions of years, not entirely unlike modern scientific notions of stars and galaxies being born and dying over eons. The Stoic philosophers of ancient Greece and Rome imagined a universe that periodically perishes in a great conflagration and then is reborn anew in an eternal recurrence. Modern science doesn't endorse an exact repetition, but echoes of these ideas can be seen in notions of cyclic or oscillating cosmologies. It's fascinating that human imagination, even before scientific data, intuited something cyclic in nature's workings. With black holes, we see natural engines of cyclic transformation. They take what exists and convert it into something new, or return it to cosmic circulation in a different form. Even in ancient mythologies and folklore, we find symbols that faintly echo the notion of powerful darkness, consuming light, and heralding a rebirth. Many cultures imagined something vast and dark that could swallow stars or the sun, a dramatic end-of-the-world scenario. The Norse, for example, spoke of a great wolf, Fenrir, devouring the sun during Ragnarok, their apocalypse. And in Hindu lore, the demon Rahu is said to chase and occasionally swallow the sun or moon, causing eclipses, though the luminaries always emerge again from his mouth. These tales personified darkness overcoming light, but importantly, they also contained the seed of renewal. The sun is reborn, a new world emerges after the old one ends. In a poetic way, black holes are a scientific counterpart to those stories. They are darkness swallowing light, yet from the cosmic perspective, the darkness might not be eternal. Hawking radiation slowly returns energy to space, and in the conjecture of new universes, the act of swallowing might be a prelude to another creation. It is a grand cosmic cycle, expressed in modern physics instead of mythic imagery, but carrying a similar message, that beyond an end, there can be a beginning. Contemplating these immense scales and cycles can be oddly comforting. It places our worries and desires into a broader context. The universe has been through so much for so long. Our brief existence becomes meaningful as part of this continuum. The end of anything, a star, a life, even the universe as we know it, might not be a final annihilation in the grand scheme, but a transition to something we can't yet fathom. Just as people find solace in the knowledge that a sunset is followed by a sunrise, one might find solace in thinking that the dark end of the universe, perhaps an endless cold night after the last star fades, could be followed by something new, a new morning in a new cosmos, if some of the speculations we've discussed come to pass. Black holes also encourage us to accept mystery. No matter how much we learn, they remind us there are horizons we cannot see beyond. At least, not yet. There is something fundamentally unknowable inside a black hole from our vantage, just as there are aspects of life and death that remain mysterious to us. Rather than causing despair, this can inspire a sense of awe. There is always more to discover, always more to wonder about. The universe, through black holes, is telling us that it hasn't revealed all its cards. In our day-to-day life, we seldom reckon with time frames of billions of years, or phenomena as extreme as black holes. But perhaps we should, at least in our imagination now and then. It stretches the mind and gives perspective that can be calming and enlightening. The problems that loom large in daily life shrink when we remember that we are on a tiny planet orbiting an ordinary star, which is just one of billions in our galaxy, which itself is one of trillions in the observable universe. A universe peppered with black holes that bend space and time, and perhaps connect to mysteries beyond. In such reflections, many people feel a sense of connection to the cosmos. We might be small, but we are made of the cosmos, and we are a way for the cosmos to know itself. We're stardust that has become conscious, the universe contemplating itself through our eyes. And part of that contemplation now involves black holes, these dark, silent teachers of humility. They teach us that even the mightiest stars can fall, that darkness can cloak even the brightest light, but also that out of that darkness, new light can emerge in time. With these philosophical whispers of impermanence and cosmic unity in mind, let's gently shift our gaze outward again to the largest canvas of all, the structure of the universe and the forces shaping its fate. Up to now, we've focused on gravity pulling things together, stars collapsing, black holes munching on matter. But there is another side to the cosmic story. The expansion of space and the great patterns of galaxies and voids that span millions of light years. Black holes are only one half of a grand cosmic balance. The other half involves vast, almost empty expanses and a mysterious push that is driving galaxies apart. This too is part of our story, a counterbalance to gravity's pull, and it will guide us toward a final contemplation of how the universe might end or transform in the eons to come. Picture yourself on a clear, dark night, far from city lights, perhaps lying comfortably on a soft patch of grass. The air is cool, and above you the sky is a tapestry of stars. The Milky Way arches overhead as a faint, silvery band, hinting at the billions of stars that make up our galaxy. In the stillness, you feel the gentle rotation of the Earth and the depth of the sky. You are ready to journey outward in imagination. Let's lift our eyes to the grand structure of the universe as it is now. On the largest scales, the universe looks a bit like a spider web or a sponge, a complex pattern of filaments and knots with vast voids in between. The filaments are chains of galaxies and clusters of galaxies. The knots are enormous clusters or superclusters where hundreds or thousands of galaxies are bound together by gravity. These structures, formed over billions of years as matter, guided by gravity, pulled together into patterns from an initially nearly uniform cosmos. Strikingly, visualizations of this cosmic web bear a resemblance to networks we see elsewhere in nature. The web-like filaments of galaxies mirror, in form, the web-like connections of neurons in a brain, or the foam-like pattern of bubbles in soapsuds. Of course, the scales and substances are utterly different, but it's intriguing to see similar patterns repeating, as if nature enjoys weaving with the same basic designs across the cosmos. At the center of nearly every galaxy, including our Milky Way, lurks a black hole millions or even billions of times more massive than the Sun. These supermassive black holes are actually tiny in size compared to the galaxy, like a grain of sand relative to the solar system. But they can profoundly influence their surroundings. When they actively accrete matter, they ignite as blazing quasars or active galactic nuclei, shooting out jets of energy that can traverse entire galaxies. In doing so, they heat up and push around gas on galactic scales, sometimes throttling the formation of new stars. Thus, black holes, though small in scale, act as cosmic sculptors. They help shape the galaxies around them. Now consider the voids, immense expanses of space where there is very little. Perhaps just a few stray galaxies, or wisps of gas in volumes tens of millions of light years across. These are some of the loneliest, most desolate regions imaginable. If you were floating in the center of one of these cosmic voids, you might not see a single galaxy in the sky, only darkness in all directions. It would be a nearly absolute dark, save perhaps for the faint glow of a far-off galaxy cluster at the very edge of sight. In that silence and darkness, you might feel a profound sense of solitude and stillness. And yet, you would not truly be alone. Space itself would surround you, and the invisible presence of dark energy would still be at work, slowly pushing the void to expand even further. Even where there is hardly any matter or light, the cosmos is still there, with you, holding you in its subtle, ever-present embrace. It's the opposite of standing near a black hole. Near a black hole, space is intensely curved and matter is ultra-concentrated. In a void, space is relatively flat and empty, with almost no matter to speak of, and only the faintest trace of radiation. Black holes represent extreme presence, all that mass in one place. Voids represent extreme absence. In a poetic sense, they are yin and yang. One is the ultimate concentration, the other the ultimate emptiness. Astronomers have even identified a gigantic region of emptiness called the Boötes Void, which spans roughly 330 million light-years, with almost no galaxies in it. A tremendous cosmic cavern, nearly empty of stars. On the other hand, our Milky Way is part of a vast supercluster of galaxies called Laniakea, Hawaiian for immeasurable heaven, which stretches over 500 million light-years and contains tens of thousands of galaxies. Such names capture the majesty of these structures, filaments and clusters of matter surrounded by immense quiet voids, making up the texture of the cosmos. What's causing these voids to grow and these galaxies to recede from one another is something physicists call dark energy. About 70% of the universe today is thought to be this mysterious dark energy, which does not clump like matter, but instead acts as a property of space itself, driving the expansion of space faster and faster. Discovered in the late 20th century by observing distant supernovae, dark energy came as a surprise. Instead of gravity from matter slowing the expansion of the universe, as many expected, the expansion was found to be accelerating. It's as if, on very large scales, a repulsive force is counteracting gravity. Dark energy is like a subtle pressure, or anti-gravity, that becomes significant when space is mostly empty and unopposed by local gravitational pulls. In the early universe, Matter was dense enough that gravity won in many regions, pulling gas into stars and galaxies. But now, with galaxies far apart and huge voids between them, dark energy is stretching the space between galaxy clusters ever more rapidly. As its name suggests, dark energy is mysterious to us. It's an unknown form of energy associated with the vacuum of space. We call it dark because we don't see it directly and truly don't know what it is. It could be an intrinsic property of space, Einstein's cosmological constant, or perhaps a new kind of field that fills space, sometimes dubbed quintessence. But its effect is clear. It pushes the universe to expand faster. The result is that voids are growing. Galaxy clusters are being pushed farther apart from each other. Over time, the large-scale cosmic web will stretch and thin out. Clusters of galaxies will become isolated islands. Already now, beyond a certain distance, a few billion light-years, other galaxies are receding from us faster than we could ever travel. Eventually, their light will no longer reach us. We live in an accelerating universe where, given enough time, each gravitationally bound group of matter, like our local group of galaxies, will be marooned, surrounded by an expanding ocean of emptiness. In the far future, an astronomer in our own galaxy, or the merged remnant of our local group, might see nothing but darkness beyond their galactic neighborhood, all other galaxies having slipped beyond the cosmic horizon due to dark energy's relentless push. This expansion, driven by dark energy, is a counterbalance to the story of black holes and gravity. Black holes pull things in, concentrating mass and energy. Dark energy pushes everything apart, diluting matter. For a time in cosmic history, gravity, forming stars, galaxies, black holes, and expansion, forming vast voids, coexisted in a sort of tug-of-war. Gravity won on smaller scales, creating galaxies, stars, planets, and yes, black holes, while expansion dominated the largest scales, creating ever larger gaps between galaxy clusters. But as eons pass, dark energy's victory will extend even further. Eventually, outside of our local cluster of galaxies, all other structures will be swept away beyond reach. It's a curious thought. In the very long run, black holes might find themselves kings of virtually nothing. Each remaining cluster of matter, like our own cluster of galaxies, might have one or several massive black holes at its core, but those black holes will have no external galaxies to interact with or devour. They'll rule over isolated islands of matter in an ever-growing sea of void. Even today, we can see the beginnings of this cosmic separation. Black holes reside in galaxies, which often reside in clusters. Between those clusters lie immense voids that are expanding. The scale of these voids dwarfs the realms of black holes. A stellar black hole's sphere of influence might be a few light years across. Even a supermassive black hole in a galaxy center affects perhaps a region a few thousand light years wide directly. But a cosmic void can be hundreds of millions of light years across. In a sense, the voids are the larger canvas on which the drama of galaxies and their black holes plays out along the filaments. The presence of dark energy and the growing voids highlights how temporary and delicate the era of galaxies truly is. We happen to live in a time where galaxies are visible to each other and the night sky is rich with stars. But the dominance of dark energy means this is a transient epoch. Trillions of years in the future, the universe will look far emptier and quieter to any hypothetical observers. Gravity pulled together matter to light the stars, and now dark energy is pulling it apart into darkness again. It's a grand thinning out that, if dark energy remains as we observe it now, will continue indefinitely. As the voids widen and the cosmos cools, black holes will ironically become some of the longest-lived and last luminous objects via Hawking radiation in the universe. In a future where stars no longer shine and galaxies have dispersed into isolated remnants, it will be black holes that still, very slowly, radiate and occasionally even collide in the dark. The contrast between a black hole's tiny, intense existence and the yawning, nearly empty universe around it will grow even starker. Having surveyed the bright beginnings, stars igniting, galaxies forming, and the gradual dimming, expansion and voids growing, we are prepared now to journey into the final chapters of the cosmic story, the fate that awaits black holes themselves and the universe at large, as the eons pile upon eons. In that distant vista, we'll find a quiet so deep and a darkness so pervasive that it truly earns the title of the final night. Yet, even in that almost ghostly end, the legacy of black holes and the structures they shaped will echo, and the possibility of new beginnings might glimmer faintly beyond. Now we drift into the far, far future to envision the twilight of the universe. Before we proceed, it's worth noting that what follows assumes dark energy remains constant and relatively mild in its effect. If, instead, dark energy were to grow in strength over time, a speculative scenario known as phantom energy, the universe's expansion could become ever more violent. In such a case, eons from now, the expansion might eventually overcome even galaxies, stars, and atoms, a hypothetical Big Rip where all structures are torn apart. That catastrophic end would occur far sooner, perhaps tens of billions of years from now, and is a very different scenario. Fortunately, current observations suggest this extreme fate is unlikely. Dark energy appears to act like a stable cosmological constant, not growing without bound. So the more plausible picture is a slow, gradual fading of structure, which we will now describe. By around 100 trillion years from now, 10 made 14 years, a 1 with 14 zeros, the era of star formation will wind down. The reservoirs of gas that galaxies use to birth new stars will be largely depleted or too spread out to condense. Existing stars, one by one, will burn out. The most massive stars will have long since exploded or collapsed to black holes or neutron stars. Medium mass stars, like our Sun, will by then have lived out their lives, becoming white dwarf embers. The universe's grand lights will steadily blink off until only the faint glow of white dwarfs, which themselves cool and fade toward black, and the occasional flaring merger of stellar remnants break the darkness. As time marches on, even those faint lights fade. White dwarfs cool to become black dwarfs. Hypothetical cold, dark spheres of carbon and oxygen ash. Neutron stars may accrete some stray matter and spark a few last flares. But they too will eventually settle into eternal cold. Planets, if any are still bound to remnants, will freeze solid or wander off into the darkness as their orbits decay or are perturbed over long timescales. Gravity continues to sculpt the scene. Over incredibly long periods, orbits within gravitationally bound groups can change. Some stellar corpses will spiral into the central black holes of their galaxies, if those galaxies haven't been thrown apart yet, giving the black holes one last meal. Others will be flung out of galaxies entirely by gravitational interactions, becoming lone wanderers through the expanding void. Galaxies themselves, in this far future, will dissolve. Take the Milky Way in the distant future. After it merges with the Andromeda Galaxy, a process that will complete in about 10 billion years, and incorporates other nearby dwarf galaxies, we'll have a larger merged galaxy, sometimes nicknamed Milkomeda. Over quadrillions of years, internal gravitational interactions will cause more and more stars, or their remnants, to either sink to the center or be thrown to the outskirts. Eventually, much of the remaining mass could end up in the central, supermassive black hole, which grows heavier with each star it swallows, or be ejected into intergalactic space. The galaxy's remnant might become a sparse cloud of dead stars and black holes, slowly evaporating as members escape one by one into the void. After an almost incomprehensible stretch of time, black holes will dominate what's left of organized matter. They will be the last substantial energy reservoirs in a universe that has gone dark. But even black holes aren't truly eternal. Courtesy of Hawking radiation, they have an expiration, albeit an unimaginably distant one. The smaller black holes will fade first, emitting their mass away over shorter timescales. But short is relative here. A black hole with the mass of our Sun would take about 10·67 years to evaporate, far longer than the current age of the universe, which is 10 years. The giants, the supermassive black holes millions or billions of times the Sun's mass, will take fantastically longer, on the order of 10 or 90-something years. For example, a black hole of 1 billion solar masses might take 10 or 100 years to fully evaporate. During this evaporation process, the black hole emits an ever so faint glow of radiation, like a cold object very slowly cooling off. Initially, this Hawking radiation is incredibly feeble. For a supermassive black hole, the radiation temperature is almost absolute zero. But as the black hole loses mass, the radiation very slowly intensifies, though even intense at the end is relative. It might become about as luminous as a small star, briefly. For most of that time, the black hole would be essentially dark to any imaginable observer. Only in the final moments would it radiate at a noticeable brightness. Picture one of these final black holes in its last moments. After eons of quiet Hawking emission, it has dwindled to a tiny size. In its final seconds, it could shine as brightly as millions of stars. A last grand fireworks display in an otherwise black universe. It might go out with a final outburst of high-energy particles and light, perhaps like a burst of gamma rays. And then it would be gone. The spot where it was would simply have a bit of stray radiation streaming outward, no bound object remaining. Envision that final outburst in the context of an utterly dark universe. It's like the last flash of a dying ember in an infinite night. After the last black hole evaporates, no bound objects of significant mass remain. No stars, no planets, no black holes, not even cold black dwarfs, if those have decayed. Some theories suggest even protons might decay after 10^34 years, though if they don't, the dark corpses of planets and failed stars could persist as quiet clumps of matter, drifting ever apart. What remains is a thin soup of particles, mostly photons, particles of light, and some subatomic particles, like electrons, positrons, and neutrinos, spread out across an immense volume. The temperature of this soup is practically absolute zero, just a whisper above nothingness. This is the heat death of the universe. sometimes called the Big Freeze. It's a state of maximum entropy, meaning all the usable energy has been used up and all structures dissolved. It is a silent, still cosmos, an endless night with no dawning day within the realm of physical time. In such a state, time itself becomes almost meaningless, with no change, no events to mark time. A second and a trillion years are almost the same. All processes have stopped or become so slow as to be imperceptible. The arrow of time, which was driven by things like stars shining and heat flowing from hot to cold, has effectively run out, because everything is at the same very cold temperature, and nothing organized is happening. One could say time has practically ended, as the universe reaches a kind of equilibrium where nothing more of interest occurs. It's a melancholic picture. A universe that began in a hot, bright Big Bang ends in eternal darkness and silence. Yet even this might not be the absolute end of the story. Theoretical physics offers a few glimmers of possible rebirth or transformation beyond this heat death. One idea is that if the vacuum state of our current universe, the baseline energy of empty space, is not perfectly stable, then given enough time, a random quantum tunneling event could occur, creating a bubble of a lower energy vacuum somewhere in the vast emptiness. This bubble would then expand at nearly the speed of light, essentially rebooting that region of the universe with new properties. In effect, a new Big Bang bubble bursting forth, consuming the old space. If such an event were to ever happen, it would be unpredictable and undetectable until it's upon us, and it would remake everything, a kind of cosmic regeneration or phase transition. Some have even speculated this might have happened before. Perhaps it's how our own Big Bang occurred, a bubble nucleating in some pre-existing space. Another speculative idea comes from cosmologist Roger Penrose, called conformal cyclic cosmology. He posits that in the extremely far future, after everything has dissolved into light, the universe might become, in a certain abstract sense, indistinguishable from the ultra-compressed, hot state of a new Big Bang. If there are no masses or distinct scales left, with only photons zipping around, the geometry of the universe at its heat death can be mathematically scaled down to resemble the beginning of a new universe. In Penrose's vision, the empty cold end of one cosmos can be reinterpreted as the fiery, dense beginning of another. Time effectively resets, and a new Big Bang occurs, starting another eon. This is highly speculative and not widely accepted, but it poetically suggests that even the final darkness might be a prelude to a new dawn. Even barring these exotic ideas, we can take solace in the fact that the journey from now to heat death is so long it vastly exceeds any timescales we can truly grasp. The universe has a tremendous future ahead. Life or intelligence, if they can somehow adapt to ever-changing conditions, might find ways to persist, or new purposes even as the stars go out, perhaps huddling around artificial energy sources or tapping into physics we have yet to imagine. Perhaps they would even use black holes themselves as a last refuge, feeding matter into them to extract energy, or gathering around the gentle heat of a decaying black hole like campers around a dying fire, eking out a final comfort from the fading embers of the cosmos. Eventually, however, the curtain must fall. In the simplest picture, we end in a forever expanding, forever cooling void, dotted only by subatomic whispers. This is far removed from the cosmos we know, full of galaxies and starlight, but it appears to be the final chapter, written by the laws of thermodynamics and cosmic expansion as we understand them. There is a profound silence to this ending. If a consciousness were somehow present to witness it, it would observe a world without form, almost a pure mathematical simplicity, just featureless space with a sparse haze of particles. Perhaps, as some suggest, this emptiness is not a true end, but a blank canvas for something new. But to our best scientific knowledge, it is the asymptotic fate, the quiet epilogue to all the drama that came before. Pondering this ultimate fate can evoke a deep sense of wonder and existential reflection. The universe begins in light, the bright flash of the Big Bang's fireball, and possibly ends in darkness, a symmetry that is stark and poetic. It's as if the cosmos breathes, an inhalation of expansion and structure, an exhalation into diffusion and silence. Whether a new breath follows remains an open question. Having contemplated the end of the universe, we come back to the present moment. Here we are, billions of years before any such end, alive and aware in a vibrant cosmos that is still in its youthful bloom compared to the ages to come. Black holes exist now alongside galaxies brimming with life-giving stars. The night sky above us is full of starlight, not darkness. It is in this fortunate era that we have the luxury to reflect, to seek meaning, and to appreciate the cosmic story unfolding around us. In the face of the far future's starkness, our present moment, and our capacity to understand and marvel at the universe, feels incredibly precious. Let us now gently return our focus to that perspective, to ourselves, the observers of this grand universe, and consider what it means to be conscious in a cosmos where black holes and endless horizons are part of reality. We have journeyed far in our exploration tonight. We began with a fundamental mystery. Whether the universe can truly forget information in a black hole, or whether some subtle accounting saves the day. We then saw how black holes surprisingly follow the same rules as heat and entropy, hinting that they carry enormous hidden information on their horizons. Through that clue, we ventured into the holographic principle, glimpsing a radical idea that our reality might be like a projection from a distant surface, with black holes illuminating how information and space-time intertwine. We delved into quantum gravity's dreams, from string theory's fuzzballs replacing singularities to loop gravity's vision of rebounding cores, discovering that even the inescapable might have an escape of sorts. We entertained the astonishing notion that black holes could be cosmic wombs, birthing new universes, an answer to why our universe is so hospitable. We imagined that perhaps our entire universe is a grand simulation or computation with black holes as its data crunchers. Along the way, we also reflected on how these cosmic ideas echo in philosophy, the impermanence of all things, the cycles of creation and destruction, and the unity of ourselves with the universe. These travels through knowledge and imagination were not just an intellectual exercise, but a meditation on existence itself, meant to inspire awe and tranquility. Even as we soared through distant galaxies and pondered cosmic mysteries, we were, in a sense, also journeying inward, discovering our own capacity for wonder, humility, and connection. The boundary between self and universe begins to blur when one realizes we are made of the universe and that it lives within us in the form of our consciousness. In exploring black holes and beyond, we are also exploring the nature of reality and our place within it. It is a deeply personal voyage, as much as a scientific one. Already, our ingenuity has allowed us to connect with these cosmic phenomena in extraordinary ways. We have recorded the gentle tremor of space-time from black holes colliding billions of years ago. Not long ago, sensitive detectors on Earth picked up a faint chirp in the fabric of space-time, the final moment of two black holes spiraling together and merging far across the universe. In effect, we turned the merger of those invisible giants into a sound we could hear, a gentle rising tone, as if the universe were whispering to us in a new way. Think about what that means. Two massive black holes collided over 1 billion years ago, creating ripples in space-time that travelled all that distance and passed through the Earth. Those ripples stretched and squeezed everything on our planet by a minute amount, far smaller than an atom, but our instruments were sensitive enough to detect it. It was as if the universe itself rang like a great bell, and we managed to listen. This achievement was not just a technical feat, it was a profound connection. We literally felt the vibrations of a far-off cosmic collision, bridging an unimaginable gulf and making us participants in events across the universe. And humanity has even captured, using a planet-wide network of telescopes, the faint image of a black hole silhouette in a distant galaxy, transforming a theoretical shadow into a visible reality. It took a global network of radio telescopes working in unison, effectively making Earth into one giant telescope to achieve that feat. The result was the now famous image of a glowing ring surrounding a dark center, the shadow of a black hole. For the first time, we saw the unseeable. That hazy ring of light, created by hot gas orbiting the abyss, confirmed that our long-held theories were true. A black hole, once an abstract idea, became tangibly visible. It was a moment when human imagination met reality, and the match was perfect. Such achievements underscore how our small civilization can reach out and touch the grand universe, forging a link between our existence and these distant, titanic events. It's incredible to think that not very long ago, on the cosmic timescale, our ancestors gazed at the stars with no knowledge of galaxies, black holes, or the Big Bang. In just the past few centuries, through science and curiosity, we have uncovered these cosmic secrets and found our perspective transformed. Yet there is so much more to learn. Perhaps in the far future, explorers, human or otherwise, will venture close to a black hole, skimming its event horizon to study it up close, or advanced telescopes will pierce through cosmic mysteries we can't yet imagine. The journey of discovery is ongoing, and we, here and now, are part of it. Each question we ask, and each insight we gain, continues the timeless tradition of curiosity that began when the first humans looked up at the night sky in wonder. In sharing this grand inquiry, we are connected to all those past and future who seek to understand the universe. Here we are, fragile beings of flesh and blood, composed of particles forged in the hearts of long-dead stars, using our minds to unravel the secrets of black holes and the cosmos. It is a testament to the power of consciousness that we can extend our understanding across such vast distances and times. We can imagine the interior of a black hole or the end of the universe. even though we have never experienced these things directly. In a sense, our minds serve as bridges across the cosmos. We carry within us a model, however imperfect, of the universe itself. Black holes, those enigmatic dark phenomena, have forced us to expand our conception of reality. They challenge us to think beyond the everyday, to grapple with infinities and quantum absurdities. In doing so, they have enriched our imagination immensely. They remind us that there is so much more to existence than what our immediate senses tell us. Just as ancient humans looked at the night sky and felt a sense of the divine or infinite, we modern humans can look at an image of a distant black hole's shadow or listen to the whisper of gravitational waves from merging black holes and feel a profound connection to the universe. It's a feeling that blends awe and humility, a sense that we are part of something far larger and older than ourselves. In the face of cosmic phenomena like black holes, our everyday concerns can momentarily fade. Deadlines, worries, trivial frustrations, they lose their grip as our perspective widens. We realize that our Earth is a tiny, precious oasis in a vast cosmos, and that we, who fret about so much, are made of the very star stuff that the universe recycles. Some of the atoms in our bodies likely came from a supernova explosion. Some neutrinos, passing through us at this moment, were emitted by distant black holes or neutron-star collisions millions of years ago. We are connected to these cosmic events in the most literal way. In a universe shaped by black holes and dark energy and quantum uncertainty, we somehow emerged, and we can reflect upon it all. This consciousness of ours gives the universe a way to know itself. In our thoughts and dreams, the cosmos is not a cold, unobserved expanse. It has an inner voice, a witness, us. There's a gentle irony. Black holes, once thought to be places where all light and information ends, have become beacons, lighting the way to deeper truths about physics and the universe. Similarly, one might think our small lives are insignificant against cosmic scales, yet we carry light within us, the light of awareness, knowledge, and love. If black holes symbolize the unknown, then our curiosity symbolizes the response of a conscious universe, striving to understand itself. We seek out the black holes in the darkness and shine upon them the light of inquiry. In doing so, we illuminate parts of our own souls. Every deep question we ask about the universe ends up teaching us something about ourselves, our limits, our creativity, our capacity for wonder. It's also worth noting the tranquility that can come from these reflections. To contemplate black holes and cosmic vastness is to engage in a kind of meditation. The mind wanders among the stars. It floats to the edge of an event horizon and peers in. It drifts through the silent voids between galaxies. In these mental explorations, we often find a sense of peace. The universe, despite its violent processes and extremes, operates on timescales and distances so grand that from our viewpoint it feels almost eternal and unchanging. The night sky above, dotted with ancient starlight, has a calming permanence, even though we know each star is evolving. By immersing ourselves in the cosmic perspective, we tap into that feeling of the eternal. We align our busy, brief lives with the slow heartbeat of the cosmos. Now, as this journey draws to a close, imagine yourself once more out under that starry sky, or perhaps orbiting serenely around a quiet black hole in the depths of space. All is still. The black hole is not a fearsome destroyer here, but a silent companion, a dark presence with a gentle pull. Its gravity is strong yet steady, holding you in a safe embrace. Around you, stars glimmer faintly in the far distance. You feel the curvature of space-time as a subtle, enveloping calm. Occasionally, if a distant star lines up just right behind the black hole, you see a delicate ring of light, the star's image distorted into a perfect circle by the black hole's gravity, like a halo briefly crowning the darkness. It's a beautiful, transient sight, a reminder that even the black hole's gravity can create graceful visions. But mostly, you are wrapped in darkness and quiet, the black hole simply a massive, silently watching presence nearby. In this scenario, you are both an observer and part of the scene, an ingredient of the cosmos, like a mote of dust in a grand cathedral of space. The black hole's presence reminds you that some mysteries remain, and that's okay. You don't need all the answers right now. It is enough to marvel, to feel, to simply be present in this cosmic expanse. We often seek meaning in stories, in beginnings and endings. Black holes gave us a story of extremes, of paradoxes and resolutions, of cycles and fate. What meaning you draw from it is deeply personal. It might be the realization of how precious and fleeting life is when set against cosmic time. It might be a sense of unity with the universe, knowing that fundamentally the same physical laws and particles dance in your neurons as in the heart of a distant black hole. It might even be a kind of release, an acceptance that change and loss, the way black holes take away the old, are part of how new things come to be, leading to a feeling of harmony with that process. In the end, as you let these thoughts wash over you, you can allow yourself to simply float in the vastness for a while. There is no rush. The universe unfolds at its own pace, and we are here for our brief but wonderful moment within it. Black holes and beyond, the mysteries will still be there in the morning. For now, you can drift. You are safe and small in the tender embrace of the cosmos, full of wonder and at peace. The stars above are like gentle guardians, their light having travelled eons just to paint the sky for you tonight. In this feeling of unity, you can let go of all worries. You are a child of the universe, resting in its vast cradle, deeply connected to everything, yet perfectly at ease in your own stillness. Nothing more is needed right now. Simply be and rest. Let your mind drift now like a beam of starlight through the quiet of space. There is nothing more you need to do. You are part of the cosmos, and this night is your gentle companion. Sleep deeply under the watch of the stars and the embrace of the universe.